Good afternoon, all. I welcome all the participants, resource persons for the last day, 6th day at FTP on Navigation with the Indian Constellation, Challenges and Opportunities 2026. Today, we are entering into the 6th day, 11th session. Now, I request Dr. N. Preeti Elizabeth to give the welcome address.
Audible, sir.
Yes, madam, please.
Okay. Very good afternoon to all. It is my privilege to introduce our esteemed chief guest. Dr. Kavitha Devireddy is an associate professor in the Department of Electronics and Communication Engineering with extensive experience in teaching, research, and industry collaboration. She holds a PhD in satellite navigation systems from Romania University and MTech in VLSI from JNTU Hyderabad, a B in ECE from Romania University, and a diploma in ECE from the State Board of Technical Education. She has over 15 years of academic experience, having worked in reputed engineering institutions such as Brilliant Institute of Engineering and Technology, VJIT, Arura Scientific Technological Research Academy, and TKR Engineering College. In addition to her teaching roles, she has industry experience as a research associate at Manjeera Digital Systems, where she worked on NAVIC modeling testing. She also has more than 5 years of funded research experience as a junior research fellow in an ISRO-SAC sponsored project focused on ionospheric time delay effect and GNSS data analysis. Her technical expertise includes MATLAB, Python, GNSS, data analysis, and signal processing. Significantly to up the advanced Romania University in collaboration with ISRO-SAC, equipped with state-of-the-art multi-concentration satellite receivers. Dr. Kavitha has published multiple research papers in reputed SCI, SCIE, Scopus indexed journals such as IET, Radar, Sonar, and Navigations, ACTA, Geophysica, Progress in Electromagnetic Research, Presidia Computer Science, and Springer LNCS. She has also presented her work at various national and international conferences, including URSI and the Pecan Satellite Symposium in Poland, supported by UWN University. She is a member of the IEEE Geoscience and Remote Sensing Society and serves as a reviewer for the Journal of Applied Geodesy. Her research interest includes ionospheric modeling, satellite navigation, and deep learning applications in communications and navigation system. Now I am inviting our esteemed chief guest, Kavitha ma'am, to take over the section. Ma'am, please.
Okay, thank you, madam, for a nice introduction. Good afternoon, everyone.
Madam, good afternoon, madam. Madam, before starting the session, I request all the participants to switch on the video for 1 or 2 minutes because we have to take the screenshot. So I request all the participants and the resource person to open the video for a few minutes.
Yeah, sure. Okay. Okay. Is it okay, sir, now?
Yes, madam. Okay, madam.
Okay. Okay. Good afternoon, one and all. Thank you, madam, for your nice introduction. Okay. Today, my topic, performance evaluation of global ionospheric models. Coming to outline, I am going to discuss the topics GNSS introduction, GNSS errors, role of ionosphere in GNSS, performance evaluation of global ionospheric models. Global ionospheric models, today I want to discuss the 4 types of models. IRI model, which is from 50 kilometers to 2000 kilometers, IRI plus 2017 model, IRI plus 2017 model with DEC assimilation, and NAEQUIC 2 model. All these models are online models. So far, I think many speakers discussed about the coefficient-based models like Klobuchar model, NAEQUIC model, NAEQUIC 2 model, and grid model. Many models are there. So all are coefficient-based models. Now I'm going to discuss these models coefficientless, means these models are not depending upon the coefficients. So we can extract the TEC values from websites, online models. Okay, this is the outline of my presentation. Coming to, sir, is it visible, sir, my screen, heading, everything?
Madam, heading is not that much visible, madam.
Okay, that's why I was,
Now it's visible. Okay.
Okay.
Now you can switch off your video because you have to save the bandwidth.
Yes. Okay. So coming to the GNSS systems, I think you are very familiar about this navigation and types of navigation systems, because since 1 week we are many speakers explained all these things. I don't want to take much time about this introduction part, only just 2 minutes. I give small introduction about this navigation, types of navigation systems, and what are the errors inside the navigation system. So first of all, what is navigation? We know very well about the navigation definition. It is nothing but determination of user position or any object at any place in the world, at any time, in any environmental condition. Either it is static mode or dynamic mode, moving object. Okay, that is nothing but navigation. It is the process of computation of user position or any object, anytime, anywhere, in any environmental condition. So that is navigation. So then how we can achieve this navigation? Then coming to the navigation systems. So there are many navigation systems are available to predict the user position. So for example, here types of GNSS. So we know the navigation system is nothing but group of satellites. So here to predict the user position, we need group of satellites information to estimate the position of a point in terms of latitude, longitude, and altitude, or XYZ coordinate system. Actually, there are two types of coordinate systems: ECEF coordinate system, Earth-centered, Earth coefficient, Earth-based coordinate system, or WGS 84 coordinate system. So according to WGS coordinate system, latitude, longitude, and altitude. ECF coordinate system, XYZ. So we can find the user position or can compute the user position with the help of satellites information, okay, in terms of latitude, longitude, altitude, or XYZ. So that is about navigation. So here the navigation systems. So we have different navigation systems: global navigation satellite system, regional navigation satellite system. So under global navigation satellite system, we know very well about GPS, GLONASS, Galileo, BEDO. And regional navigation satellite systems, IRNSS, or it is renamed as NAVIC by our Prime Minister Narendra Modi ji, and it is India, and QZSS. So it is maintained by Japan country. Okay. So these are the frequency bands, GNSS frequency bands. So different navigation systems are maintaining different frequency bands. L band. So coming to 1164 megahertz to 1614 megahertz. So from lower band to upper band, all constellations are covered here: GPS, GLONASS, Galileo, BeiDou, IRNSS. So this is complete L band only. And NAVIC system also, and it transmits, NAVIC satellites also transmits the two types of signals, L band and S band. There is one reason why we go for S band is this one only, because complete L band is occupied by all the constellations. There is no sufficient space in the L band. So then India, then we go for S band frequency. So that is about the small introduction about GNSS navigation, definition, and why navigation system. Okay, now coming to GNSS errors. So practically in any field, if you want to design any system, but 100% accuracy is not possible. it is not possible 100% accuracy. If you take any field like a VLSI chip or any communication system, navigation system, any system, 100% accuracy is not possible practically, because the system, the parameters are influences the system performance. Similarly, in GNSS field also, the user position is degraded by many parameters. So your user position means, suppose my location is at 2 comma 2 comma 4, for example, x comma y comma z, 2 comma 2 comma 4, but the predicted position is some 2.1, 2.1, 4.1, means some deviation is there, means it is not possible to get the exact location of mine. So because of some degradation factors are there in the DNS system. So for example, if you take satellite clock error, orbital error, ionospheric error, tropospheric error, receiver error, multipath reflection. So already all these errors are discussed in, I think, in your previous session. Just give small introduction about each and every error. Suppose if you take satellite clock error, which is due to because of clock, because in satellites, rubidium clocks, it is very costly clock. Rubidium clocks are used in satellites. But coming to receiver part, so receiver part means ground segment part. In receiver, we are using crystal clocks. So there is some unsynchronization between satellite clock and receiver clock because of the materials the made up of is different. So because of unsynchronization, there is a small drift in the clock. So that gives satellite clock error. That error is very, very small error. Means if you take this pie chart, 18% contribution from satellite clock error, 18% contribution to the total error budget. Okay. Next, orbital error. Orbital error means, so when satellite is revolving in a orbit, due to the gravitational forces, sometimes there is a small drift in its position. It is deviated from its original position in the orbit. So that deviation causes some error. So whenever the deviation occurs, immediately the master control station receives that information and they will correct that position of that satellite. So, but that error is called orbital error. Its contribution is 22.12%, but it is immediately corrected by the master control station. So there is no problem about orbital error. Okay. But satellite clock error, we can't change the material of the satellite clock and receiver clock. Some mathematical algorithms we need to omit that error. And coming to multipath reflection. Multipath reflection, we know very well in communication systems. Whenever there are tall buildings or mountains, the signal is reflected. So actual direct path is this one, but because of tall building, the signal takes some reflection. So the traveling time and the path, the distance is more. So it introduces some delay to the error budget or user position. So that type of error is called multipath error because of the reflection. The contribution of multipath error is 8.84%. So it is also, we can mitigate using mathematical algorithms, and its contribution is very less compared to the others. And also we can omit this error using mathematical algorithms. Okay. Next, coming to receiver error. Receiver error, we know very well about, very well. Receiver is nothing but one electronic device. Inside, what will be there? Electronic circuitry. Obviously, the electronic components are temperature dependent components. It introduces some noise in the components. So because of that noise, it enters some, it contributes some errors. That error is called receiver error. That receiver error, the contribution is only 2.65%. And coming to tropospheric error, these two errors are called atmospheric errors. Tropospheric error, ionospheric error. Tropospheric error, we know the layer exists from 0 to 50 kilometers only. So up to 50 kilometers in atmosphere, due to the temperature and humidity factors, it refracts the signal. When the signal is transmitting from the satellite to the receiver, some refraction will happen in the tropospheric layer because of temperature and humidity factors. So this contribution is 4.42%. So there are also models are available to mitigate this tropospheric error. Its contribution is also very less, 4.42%. So we can omit that error up to 1%, not exactly zero, but little bit better, 1%, 0.5%. Like that, we can reduce the tropospheric error using mathematical models. And the next, coming to the ionospheric error, the most predominant error in GNSS is ionospheric error. So why? Because all these errors are, we can mitigate using mathematical models, because some static rules are there. So we can apply the algorithms, we can change. But coming to the ionospheric error, there is no fixed model. So far, no, none of the scientists, none of the constellation did find the fixed model to the ionospheric error, because we know very well about ionospheric layer, because it consists of some electron density. That electron density is not uniform throughout the world, throughout the globe, because it varies, depends on so many parameters like low latitude, high latitude, mid latitude, and seasons, day times, during night time, daytime, and some geomagnetic storms. So many parameters are there. So that's why this ionospheric behavior is not a constant. So that's why we can't predict the exact TEC for so and so place, because it depends time to time. So that's why there is no fixed model to mitigate this ionospheric error 100%. So that's why continuous investigation is necessary for modeling of ionospheric layer or ionospheric delay. So this is about GNSS errors. So now coming to, so all errors are okay, we can mitigate, but this ionosphere continuous investigation is necessary. So here my part today, I am going to discuss ionosphere. Why? What is the relation between ionosphere and signal delay? So before going to that, the role of ionosphere in GNSS. Even small variations in electron content of the ionosphere can cause errors of several meters in the computation of user positioning. So that's why we can't neglect this ionospheric delay. Sometimes when we book a car, sometimes it is showing the location 20 meters away from your original location. That 20 meters error is because of all these errors. Tropo, ino, clock errors, any errors. Okay. So, but out of all the errors, this ionospheric error is the most predominant one. Suppose 20-meter error is there in your original position, maximum 10 to 15 meter error because of ionospheric delay only. The rest of 5 meters because of all other components like clock errors, satellite clock errors, tropospheric, receiver noise, etc., etc. Okay. So this ionosphere not only GNSS communication, it also affects other fields like HF radio communication, satellite communications, radar and remote sensing, and space weather monitoring. Okay, so we know very well about this ionospheric layer. This ionosphere is the upper region of the its atmosphere. It exists between 60 kilometers to 1000 kilometers roughly. So actually 2000 kilometers, but roughly this effect will be from 60 kilometers to 1000 kilometers. So it contains ionized particles, free electrons like free electrons and ions produced mainly by solar radiation. Because of these charged particles, the ionosphere strongly influences radio wave propagation or satellite navigation. So this diagram shows the simple ionospheric layer part. Okay. So before going to this ionospheric delay estimation, we have to know some terminology. So relation between ionosphere and refractive index of the ionosphere, ion density, total electron content, speed of the signal, speed of the light, frequency of the signal, time delay in nanoseconds, range delay in meters. So these are the terms we have to know before calculating the delay of the navigation system. So coming to first, the relation between refractive index and ion density of the ionosphere. We know all these formulas very well from our physics background. Once again, I recall this one. you can calculate refractive index, approximated refractive index according to Appleton equation. N is equal to 1 minus 40.3 into ion density. Ne means here electron density by F square. So F is nothing but frequency, signal frequency. This 40.3 constant comes from physical plasma parameters. Actually, the derivation is there by considering group velocity, phase velocity, all those things. We derive the equation. The equation is N is equal to 1 minus 40.3 into ion density by F square. So from this equation, here it is clearly we can say ion density is changing means the refractive index of the medium is also changing. So in the ionosphere, if the electron density ions are changing, the refractive index is varying. The resultant, the signal, whenever the signal is passing through that particular part, it is some bending will happen in the signal. So bending occurs means obviously some delay comes into the picture. So that is the thing here. Interpretation, you can say if electron from this equation electron density increases, refractive index of that medium is changes. Lower n means the bending is more. So this slide represents the relation between refractive index of the ionosphere and electron density. So your conclusion is refractive index is not uniform in the ionospheric layer because of the varying of the ion density in the ionosphere. So that is the main reason we are getting the delay in the user position. So we know according to Snell's law, refractive index changes means with altitude or medium, the signal bends. So here this graph shows if altitude is changing, increasing, the refractive index of the medium is decreasing. And also here in this diagram, the refractive index when signal is transmitting from the satellite to the receiver at this particular portion N3, N4, N5, here refractive index variation is more because at this particular point electron density distributions are irregular because the previous studies from literature and ionospheric studies, the thing found is in the ionospheric layer at 350 kilometer, the ion density irregularities are more. This is the standard point from literature. Okay, so that's why in ionospheric layer, this part refractive index variations are more. It is not uniform. So the signal bending is more at 350 kilometer height, not exactly 350, some 300 to 375, 400. In between that period only the signal is more degraded by the layer because of this variation of refractive index. Now coming to the next parameter, relation between ion density and total electron content. Total electron content represents the total number of free electrons integrated along a path between satellite and a ground receiver. So that's why here the equation is taken as TC is equal to integral of ion density. So generally this TEC is measured in terms of 10 to the power TECU. 1 TECU is equal to 10 to the power of 16 electrons per square meter. In next slide, I will explain how the contribution of TECU to delay. So TEC directly quantifies how much a radio signal is delayed or refracted as it travels through the ionosphere. Higher TEC means the delay is also more. So this picture indicates when signals are transmitting from here, two different frequency signals are transmitting from the satellite to the ground station, means a receiver. So in between, in ionospheric layer at 350 kilometer height, the signals are disturbed because of irregularities of the ionospheric layer. Here we can observe one thing, important point. we know in GPS satellites are transmitting in two different ways. Two signals, L1 signal, L2 signal. So L1 signal frequency is greater than L2. So here the point is high frequency signals are less influenced by the ionospheric irregularities compared to the low frequency. This picture clearly showing that L2 is more influenced by L1. So in navigation system, if you go for high frequencies, we can reduce this delay little bit. But consequently, other problems will occur when we go for high frequencies. Now, the relation, so far we discussed the relation between refractive index, ion density, and TEC. Now, coming to how this TEC affects the range delay or ionospheric delay. Range delay is measured in meters, time delay is measured in nanoseconds. We know the basic relation here. You can see ionospheric time delay tau is equal to 40.3 by C into F square into TEC. So there is a derivation. The derivation is available in Kaplan textbook. Here I written direct formulas. 40.3 by C into F square into TEC. So TEC, this time delay, both are directly proportional. So this is measured in nanoseconds. Now, user position means it is always measured in terms of meters only, not in nanoseconds, meters. So when we converting into the meters, that is called range delay. R is equal to 40.3 by F square into TEC. When this C into tau, nothing but R, distance, is equal to this one. It is measured in meters. So this is the basic formula to calculate the delay. How much, how many meters are affected by the TEC. Here I can explain one simple table. So here NAVIC L5, we know very well about the frequencies. NAVIC L5 frequency 1176.45, NAVIC S1 signal 2.4 giga or 2492 mega, GPS L1. So if you are calculating the delay for these frequencies by substituting in the above formula, if you take NAVIC L5 signal, L5 means in place of F, you substitute 1176.45 in equation 1. Then it gives 0.2262 meters. So this delay means because of one TECU unit, only one TECU unit. One TECU unit means 10 to the power of 16 electrons per meter square. So because of one TECU, it contributes 0.2262 meters error in the user position when you consider NAVIC L5 signal. So same thing, if you convert it into nanoseconds, how much time? 0.97 times extra time it takes to reach the ground because of only one TECU. Similarly, if you calculate for GPS L1, it takes 0.06. So NAVIC S1 signal 0.004 and time delay 0.21 nanoseconds. So one TECU contributes this much of error. Then you think, suppose this is only minimal value. Now we think if in ionosphere, suppose 100 TECU are there. 100 TECU means 100 into 10 to the power of 16 electrons. So when signal is transmitting across the ionosphere at that particular point, if 100 TECUs are there, so that content, how much it contributes to the user position error. So 0.22 into 100 TECU means 22.62 meters error. So it is not acceptable error at all in navigation system. 22 only because of 100 TECU. So 22 meters for NAVIC L5, for GPS L1 6 meters, and for S1 signal 4 meters. For S1 signal, it is very less big compared to other signals because S1 frequency is very high frequency. So we discussed already, high frequency signals are less influenced by the ion density. So because of that, here we are getting only 0.004 for 1 TECU. So that is the advantage of NAVIC S1 band signal. Okay. So this is the basic thing, how the ionospheric layer introduces the position error to UERE, user equivalent range error. So this is only single frequency and dual frequency. Above we discussed this formula. This is only for single frequency because satellites can transmit multiple frequencies. Suppose if you take NAVIC system L5, S1, GPS L1, L2 like that, multiple. So if you take only single frequency, you can calculate the time delay using the above formula. Some receivers are dual frequency receivers. In dual frequency receivers, will take two frequencies. The advantage by taking dual frequency receiver, the user position is less than 1 meter. For single frequency receivers, 5 to 15 meters. Because in dual frequency receivers, TEC is calculated directly using dual frequency algorithm. Later we'll discuss this part. For single frequency receivers, all these are model based. We are using one model to predict the TEC. After calculating the TEC, we are subtracting the TEC delay from the overall UERE. Then we'll get the actual error. But this error is compared to dual frequency, it is much more. 5 to 15 meters here it is less than 1 meter. So performance for single frequency is poor, dual frequency good. But the thing is, cost of the dual frequency receiver is very high. So for civilian purpose, we are using only single frequency. Only for precise applications only, we'll prefer dual frequency receiver because of its cost and complexity. So why I explained this slide means, so the above formula is only for single frequency. Now coming to the dual frequency, the TEC, how you can calculate the TEC using dual frequencies. This is the formula. The TEC is, again here in TEC, there are two types of TECs, slant TEC, vertical TEC. Slant TEC is nothing but the electron content along the actual slanted path from the satellite to the receiver. So direct from satellite to the receiver, slant path. So that is calculated by 1 by 40.3. This 40.3 is the constant from the derivation we'll get. Here we are using two frequencies in dual frequencies. That's why F1 square, F2 square by F1 square minus F2 square into P2 minus P1. So F1, F2 are the frequency of the signals which are transmitted by the satellite. If you consider NAVIC system, we have two signals. The satellite, NAVIC satellites transmits L5 signal, S1 signal. P2, P1 are the pseudo range observables of L5 and S1 signals. So these two values are available from navigation message only. So direct by substituting these values, these are fixed. F1, F2 are fixed. P1, P2 are varying from satellite to satellite. You take in NAVIC system, we have present, we are receiving 5 signals from NAVIC receiver. So from satellite to satellite, these values are varying. The TEC value is also changing. So this is about slant TEC. So vertical TEC is nothing but the total electron content along a vertical line from the receiver straight up through the ionosphere. So here in this diagram, you can see the difference. This is Aztec satellite to the, this is receiver point. User means here lambda 5, latitude, longitude, user point. So from satellite to the receiver, this is called slant path, and the corresponding TEC is called STEC. This is the intersection point, IPP, ionosphere peace point. It is defined as the intersection point where the satellite signal intersects the ionospheric layer at the height of 350 kilometer only. We are considering 350 because our studies, ionospheric studies tells us at this height only density is more, irregularities are more. So that's why we are taking IPP point at 350 kilometer height only. But the problem is when we are calculating slant TEC, here exact TEC, we are unable to calculate exact virginal TEC because suppose elevation angle of the satellite is very low, the distance traveled by the signal is more because of the low elevation angle. So here when we are calculating the delay, some elevation dependency is also there. Means the total delay is not only because of STEC, also contribution, elevation angle contribution is also there. So that's why to separate the effect of TEC, then we go for VTEC. The need for VTEC is to calculate the pure TEC, the signal which is affected by only TEC, to avoid the dependency of elevation angle of the satellite. So that's why we are calculating VTEC. So this is the formula to calculate VTEC from STEC. So after calculating STEC, it is multiplied by 1 minus RE into cos E by RE plus HS. RE means, in this diagram you can see, RE means radius of the earth. And cos E means here elevation angle of that particular satellite. HS is the height from user to IPP point. So this is the data we require to convert from STEC to VTEC to avoid the dependency of elevation angle of the satellite. And this function is also called mapping function. Okay. So after calculating VTEC, next our aim is delay calculation. If you know VTEC, you can calculate delay from the basic formula. We know the formula TEC into 40.3 by F squared. So this is for single frequency only. So dual frequency, the frequency, two frequencies we are using. So in single frequency, suppose if you want to calculate the delay because of only L5, then you substitute L5. Only S band, you substitute S frequency. So this is the formula of vertical ionospheric delay. So now so far we discussed the relation between ionosphere and different parameters, how the delay affect by ionosphere. The parameters are, the main parameters are here: refractive index, ion density, TEC, STEC, and VTEC, frequency of the signal. So this is about mathematical relation. Okay. So now coming to this ionosphere, as we know, ionosphere is highly dynamic and variable. So highly, it is not a static layer, it is a dynamic layer. The refractive index, ion density, everything is changing. So the TC is also, it is a not constant parameter. It also depends on so many parameters. So this slide says the ionosphere is not static, it changes with what are the parameters? Time of day, daytime ionization, nighttime recombination. We know daytime ionization takes place, so electron density increases. Nighttime recombination takes place, so daytime electron pairs are increased. That level is increased because of the ionization. Electrons increases means obviously our refractive index is varying. So that is one reason. Time of day. Seasons. There are equinox, solstice, different seasons are there. The seasonal variations are also happen in the ionosphere. And latitude. Latitude means stations. The same TC is not, suppose if time is 2 o'clock, but if you take Bangalore, Hyderabad TC is different, Bangalore TC is different, because the station lat longs are different, the ionospheric is different. There may be some rainy is coming, but in Hyderabad sun is there. So because the so many parameters, so here latitude. So for any two stations, we can't say ionospheric is same. Weather changes are there, season to location to location. And solar cycle, we know 11-year solar cycle is there. The solar cycle, the intensity of the solar radiation is varying from cycle to cycle. 11 years, if you take 11 years, from year to year, the solar intensity is changing. The solar intensity is changing means again it affects the TEC values. And one more factor, geomagnetic disturbances, storms. So because of the storms, so geomagnetic disturbances will happen. Obviously, it affects
Trial.
in the ionospheric layer. So this ionosphere depends all these parameters. So that's why hence there is a necessity of continuous investigation and analysis of ionospheric time delay effects of navigation signals, where the dynamics of the ionosphere is very complex. And especially These TEC variations are more intense over low latitude regions due to equatorial ionization anomaly. If you take this globe, so equator, the red part, the regions which are nearer to the equator are more affected by EIA effects because near the equator, magnetic field effects are more. Some E cross B fields will be developed. This field obviously influences the ionization levels in the ionosphere. The regions which are nearer to the equator are more affected by ionospheric delay effects compared to higher latitudes. So here quiet and disturbed day. This is also one term we how to know. Time of day, these are the basic things. Okay, here quiet and disturbed day. So the days are dividing into two types: quiet days, disturbed days. For every 1 month, for every month we have 5 most quiet days, 5 most disturbed days. These days are declared based upon the parameters KP index and DST values. These values are available on the tutor side. Based on the parameters, we can the table also available on the site. So which one is the quiet day, which one is the disturbed day? So when we are going to work on this ionosphere, so first we have to select quiet days, disturbed days. The research is in different way. For quiet day, I know the TEC effect is different. For disturbed day, the TEC effect is different. So that's why when we are working on this ionospheric delay, so day wise also we need to analyze TEC contributions. So that's why here we are taking quiet day, disturbed day. So what is mean by quiet day? A day with low geomagnetic activity and stable ionospheric conditions, resulting in smooth and predictable TEC and minimal ionospheric delay. So the geomagnetic indices such as KP less than 3, DST value 0. So that day is considered as a quiet day. Disturbed day with high geomagnetic activity, where the ionosphere becomes highly variable and rapid TEC fluctuations will happen. The KP value greater than or equal to 4, DST significantly negative. So these two parameters are the measuring parameters to say the day is quiet day or disturbed day. Based on this, we have to select the days while going to the research. So this is, so far we discussed only the basic part, how ionosphere affects. Now coming to IRI model, global ionospheric models. So I tested IRI 2016 model with the NAVIC GPS GLONASS data. So before going to that IRI model, first of all, we have to test our observation data. So here I evaluated NAVIC signals over Hyderabad station. So this is the experimental setup. When I was in PhD, I used the data, Osmania University data. There, ISRO sponsored 2 receivers. These 2 receivers are mounted on the rooftop of the building, and these are indoor units. And this GUI, this observation data, actually I used in my research. So here, complete 1 week data we analyzed. This is only for testing purpose. First, before going to the research, first we have to test the signals, observation data for NAVIC system only, this one, because GPS, GLONASS, Galileo already well established systems. NAVIC is under testing phase only. So that's why I evaluated IRI model with NAVIC data. Before that, I analyzed the NAVIC data from Usmania University, Hyderabad station. So complete 7 days data. I plotted here simple elevation and azimuthal angles. The whatever the data I collected from the receiver, just I plotted in the MATLAB just to test the signals, visibility, continuity. So here we know very well about in NAVIC 3 are geostationary and 3 are geosynchronous satellites. So here clearly you can observe for geostationary elevation angle deviations are very less because it is stationary. It is located in stationary orbit. For geosynchronous, the elevation angle changes from minimum above 30 to maximum 70, like that. Similarly, azimuthal angle also you can see here for geostationary and geosynchronous satellites. Similarly, we verified signal strengths of the satellite signals, 6 satellites and their signal strengths. All the signals are maintaining good signal strength greater than 40 dBh. So our system is perfectly working. So we can use this data to evaluate the models, ionospheric models. and also visibility plots. These are the sky plots, visibility of NAVIC satellites over Indian region. Here 5 station data we collected. So to evaluate the performance of NAVIC over Indian region, we collected 5 stations data. So in 5 stations, we observed 6 satellites at that time. Actually, this data, 2017 data. At that time, we received 6 signals from 6 NAVIC satellites. So for all stations are receiving satellite, there is no discrepancy in the visibility. Continuous visibility is there. Continuously, we are receiving the signal. So we can use this data in determining the user position and ionospheric analysis. Now coming to our topic. So Aztec VTech. So this first graph, it indicates slant total electron content due to all IRNSS satellites, 6 satellites. So this is slant TEC. The B diagram indicates vertical TEC. So here it is clearly I mentioned why we are converting Aztec to VTech, because to avoid the elevation angle dependency. If you compare these two diagrams, suppose if you take this one 1G satellite, coming to Aztec 1G value is very high. Here you can say 80 TECU. So very high. When we are converted into VTech, that value is reduced because the difference between this Aztec and VTech, the TEC is because of elevation angle only. Here 80 TECU it is showing maximum, but in second graph it is showing only like 30 to 40. In between it is varying 30 to 40. In the sense, the 50% of TEC is because of the elevation angle of 1G satellite. Because in previous diagram, we observed for 1G satellite, the elevation angle is very less compared to all the satellites. Here it is below 30. It is varying between 25 to some 32 like this. So because of that, it contributes more Aztec value. So that's why VTech is, we have to convert Aztec into VTech to avoid that elevation angle dependency. And after that VTech calculation, we calculated vertical ionospheric delay of all the satellites. So 1B satellite contributes how much ionospheric delay over a period of 24 hours. Here the data only for 1 day, here I plotted. So throughout 24 hours period, so IR, suppose if you take 1B satellite, how much delay it contributes to the position. So from 0 to 24 hours. But y-axis vertical ionospheric delay, the maximum delay is 12 meters. If you take only one satellite, 1B satellite, 12 meters of ionospheric delay, it is generating. So it is maximum during afternoon hours only. We know ionospheric density during daytime is more, nighttime it is very less. Because of that only, the delay graph we are getting like this. During early morning hours, night times, the delay is very less because of recombination takes place at that time. During afternoon periods, the delay is very high. So this is only for observation data, real-time data, satellite data. From direct satellite data we are collecting. Okay, that is day variation. So we discussed one point in previously. The ionosphere depends day, months, seasons, and solar cycle. So in this graph, we tested the daytime, nighttime, during daytime, it is not uniform. Electron density is not uniform. Coming to this monthly variation of VTech due to NAVIC signals over Hyderabad region. During this is complete 2017 data, 1 year data we have collected. For every month, 5 most quiet days and 5 most disturbed days we collected. For those days only we tested. Because this is only, it is enough to take 5 quiet days and 5 disturbed days. The other days we no need to take that because average TEC will be get the same manner. Okay. So if you observe in this graph, with respect to UTC time, January to December, the equinox months like March, September, the few months are contributing more VTech value. Suppose this graph in September month showing highest TEC value. This is quiet days, disturbed days. When we compare these two graphs, compared to quiet days, in disturbed days, the TEC values are little bit more, not much significant difference is there actually between quiet and disturbed days, because here consider year is a low solar activity year. 2017 year comes into the low solar activity year. Because of so low solar activity, for disturbed days, not much significant difference observed between quiet days, disturbed days. Suppose if you take high solar activity year, maybe there is a huge difference between quiet days and disturbed days because of the geomagnetic storms or solar activity period. Okay, but in our research work we observe only less difference between quiet days and disturbed days. So, and also we plotted contour plots, quiet days and disturbed days. So the between 8 o'clock afternoon, 8 to 12, it is UTC time actually. So UTC time, local time means difference is 5.5 hours. So UTC, suppose if UTC is here 8 UTC means in our India local time, if you convert it into IST plus 5:30, you add 8 plus 5:30. So 12, 13:30 means 1:30, exactly mid afternoon, 1:30 to 12. 12 means again evening, 4 o'clock, like that. So this period only the density levels are more. It is clearly you can observe in this contour plot. So TEC 40 to 45. This period we observed for quiet days. Disturbed days also the same thing. But compared to quiet days, little bit TEC distribution is more compared to quiet days. So here you can see. And in for disturbed days, there is a discrepancy. Means the patches are happens. So we know obviously in disturbed day geomagnetic storms will occur, because maybe due to that only here we are getting some discrepancy patchway. So this is monthly variation of VTech, vertical TEC. Similarly, the same data, seasonal variation. If you take seasons, March equinox, June solstice, September equinox, December solstice, quiet days or disturbed days. Clearly, you can see in disturbed days, the deviations are more. So September, June and December solstice, the VTech value maximum we observed at 30 TUC, near closer to 30 TECU. But for equinox months, the difference is, the point is the maximum peak TECU point is at 40. This thing observed for disturbed days during low solar activity. But in quiet days, not much difference compared to disturbed days. See here, this graph. So similarly, contour plots for quiet day, disturbed day. Here also you can see seasonal variations. For equinox seasons only we are getting much TEC values. So the previous slide only, it indicates how the ionospheric delay is varying day, hour to hour and day to day and month to month and season to season. Now coming to frequency dependency. So ionospheric delay, we discussed the point. Ionospheric delay depends on the frequency. So that's why to test that one, here we collected two signals data, L5 signal data and S1 signal data, complete 1 year data. We plotted TEC ionospheric delay values. Here it is clearly, we can say, for S1 signal, ionospheric delay values are very less compared to L5 frequency signals. If you take in the month of January, the maximum peak delay is at 2 meters only. But for L5 signal, it is more than 8 meters. Similarly, in equinox month, September, during equinox months, ion density is more. That's why low frequency signal is affected by more. That's why here we are getting 12 meters delay. But whereas for S1 signal, some 2.53 meters. So in compared to all the months, in equinox months only, we observed more delay. This is also for quiet days and disturbed days. So for example, if you take for L5, maximum value 4.13, for S1 signal 0.92. So this is the advantage of high frequency in the context of ionospheric delays. Not only NAVIC data, and we validated that NAVIC data with other constellation data also, estimation of VTech due to GPS and GLONASS also. So in GPS also, we observed the same similarities, same irregularities and same pattern. Similarly, we plotted for 3 constellations parallelly, NAVIC, GPS, and GLONASS. The similar way of changing is same in 3 constellations, but in NAVIC a little bit variation because of the NAVIC is a regional constellation. Maybe that will be the one of the reason. And correlation between 3 constellations, but almost correlation is good. The 3 constellations are maintaining same means the 3 constellations predict the same contribution of TEC in the ionosphere. So you can use any constellation data in our research. So now coming to the IRA. So coming to now the models, global models. So we know there are plenty of ionospheric models because it is not a small factor. Ionospheric delay is not a small factor. Continuous investigation is going on since so many years. So many models are there. Just I show you the tables only. Don't I want to go in detail models. IRI model, IRI plus model, NICVIC G, bent model, and Klobuchar. Different constellations are using different models. GPS Klobuchar model, NICVIC Galileo, BEDO, VDGAM, multiple NTCM, like that. The assimilative means here the categorized. These are empirical model. This table shows empirical or climatological model. Means it is a not real-time model, just climatological models. These are broadcast or GNSS signal frequency model. Means these models depends on the coefficients. The whatever the data we are receiving from the satellites navigation data, we need coefficients to perform this model. So these models are dependency models. And these are assimilative or physics-based models. So assimilative. So to improve the model performance, some assimilation, external input we are giving to the model. So then we get the fine result. And TEC map-based or operational models, GIM maps, STEC models, TEC from madrigal models, machine learning. Nowadays, we know very popular, the machine learning AI models are very popular for any field. So in GNSS also, the people are using machine learning and AI models. The present trend is going in this area only. So out of all these models, but navigation systems for single frequency receivers, they are using fixed models like GPS. The GPS receivers are designed inside the receiver. They are using Klobuchar only. Galileo, NICVIC G, BEDO, BDGAM, NAVIC, grid model, Klobuchar. 2 options are available in NAVIC receivers. Either you can connect grid model or Klobuchar model. And GLONASS, Klobuchar. So these all coefficient based models are using in present existing navigation system. The other models are only for research point of view, only for testing, to test the validation of the models. But practically in real-time receivers, the people are using, the developers, the company manufacturers, they are using these models only inside the single frequency. This is only for single frequency receivers. But dual frequency, there is no need to use the model, direct algorithm, this one, STEC calculation, F1, F2 square. So this formula, this algorithm nullifies the TEC value. Direct to accurate TEC, we can detect the TEC, that resultant ionospheric delay, we can subtract from the overall delay, the algorithm. That is fine. But the problem is coming to single frequency users. So they are using these standard models. All these are coefficient based models. So already we discussed about this table. Now coming to IRI, International Reference Ionosphere Model. So this is an empirical climatological model. The application, actually in real-time receivers, we are not using this model, but the significance of this model is only for testing and validation to predict the TEC. And recently one paper published by ISRO scientist Rajat Acharya sir, he clearly say one point that IRI model is a climatological model, but we can use this model in receivers also. How? The sense, sir found the points when sometimes in sea environments in remote sensing areas, sometimes there is a loss of signal navigation in the absence of navigation message, then to predict the TEC, this type of model we can use because it does not depend any coefficient, this model. But Klobuchar model, grid model, every model, it depends on the navigation message, satellite information. Sometimes at sea environments, remote sensing areas, in the signal absence is there, then to predict the TEC at that particular point, we can use this model. The IRI model, it does not give the accurate TEC, but in that scenarios, you can use this model to predict at least approximate TEC to predict the user position. So that point, sir, in that paper, sir found that result actually. And this model actually predicts the TEC from 50 to 2000 kilometers. So these are various versions of this IRI model since 1990 to 2024. Present 2020 model they are using, 2024 pre-released, but in online it is not available. Researchers still they are using IRI 2020 model. So actually in my work I evaluated IRI 2016 because that work done in the year 2019 that period. So recently I found one paper also from Delhi University. They published to evaluate the performance of 2016, 2020 and e-quick model. If time permits, I will show that paper also. So actually these versions are updated based upon the inputs to this model. To update is workshops, symposiums, seminars, and publications. When we are publish the papers based on this model, they will take the inputs from our papers only, standard papers, SCI publication like journals. Okay. So based on the inputs for every 4 years, they will update the model. Every year they are conducting one workshop in different countries. There the people will discuss what are the changes we have to made in next release of the model. So that is the thing will happen in the IRI development. One team, Kaspar Ursi team, they will conduct the seminars. So now I am using this model here actually. This is the flow chart, how I follow the steps to evaluate the TEC for here calculation of IPP points using Klobuchar algorithm. IPP point by substituting IPP points in IRI model. No need to calculate IPP points. Direct station lat lungs also we can substitute in the IRI model. We can predict the TEC values. And right side, this is VTech values from the observation data. In this work, we compared the IRI model TEC and this NAVIC observation data, GPS, GLONASS, NAVIC data. And statistical analysis by taking three statistics parameters like SKLD, CC correlation, linear metric distance. These three parameters I considered to evaluate the model. Before that, we checked for visibility of three constellations. So before going to analysis, first we have to do one thing. First, consistency of the signals. So here GPS, GLONASS, and NAVIC signals, we tested the visibility for different PRNs. So we received the good signals. So we consider those one, and this is the sky plot of three constellations. IPP points, this is the mathematics which is used to calculate IPP points at 350 kilometer height. These equations are taken from Klobuchar algorithm actually. So IPP points plot for three constellations. For every satellite, we calculated IPP points. Those IPP points we substituted in IRI model and we predicted the TEC for individual satellites. So these are the metric performance parameters. This is only theory part, the direct formulas. By taking probability density function of model TEC and observed TEC. By taking two PDFs, we evaluate the metric performance. So why I consider these parameters generally in papers, RMSE, mean value, average value, like that the people will take. Actually, initially, I also took those formulas, but when I published this paper in IET, one of the reviewers suggested me why you are using RMSE and mean values because ionosphere is a dynamic layer. It is changing. So if you take RMSE, it is not the correct factor to analyze the model performance. He suggested me. So that's why I preferred SKLD, cross correlation and metric norm, these three parameters in this work. This is the final result after calculating and substituting the model from January to December. NAVIC TEC, IRI TEC. The first graph, NAVIC TEC, blue color, the red color, IRI TEC. So in most of the cases, IRI model for NAVIC data, IRI TEC follows the observation data. Similarly, with GPS, GLONASS. So three constellations. IRI model is following the three constellations data. Small differences are there. Those differences we can say from statistical analysis. This is the first one is for quiet days. The same scenario we followed here, quiet days, disturbed days for every month, month-wise, seasonal-wise. In previously, I explained only observation data. Now we included model data also. We verified the model data with the TEC, with the observation data. This is quiet days. So this is the metric performances for three constellations. Direct, I explain the conclusion for this part. So GPS, IRI model. When IRI model, GPS, these two are used. Cross correlation values are 0.86 and 0.83 overall for disturbed days. L2N 0.04, 0.05, SKLD 0.12 and 0.14. Similarly for GLONASS and NAVIC. So compared to these three constellations, NAVIC constellation for NAVIC data, IRI model is giving better values compared to these three. If you compare 0.89, 0.90, because NAVIC is a regional constellation, we calculated IPP points. So there is not much deviation between the IPP points. So because of that closer points, maybe the IRI model is giving good result compared to the other constellations. 0.03, 0.04, 0.11, 0.13. So this is the scenario. We evaluated the model, International Reference Ionosphere model with three constellation data. So this is the contour diagram. From this diagram, here it is clearly you can see the variation on x-axis, months, on y-axis, different observation data and their corresponding model TEC values. You can see for quiet days and disturbed days, the TEC distributions. So these results we published in IIT radar and sonar paper, validation of IRI model with Indian NAVIC data for future navigation applications. So in the sense, we can use IRI. So actually, I can say one point for researchers. So using these INO models means online models, there is a lot of scope for research. So because the day-to-day seasonal variations here, we can take any year data. So not only current year, the previous year's data also we can take, we can validate these models with any constellation data. So nowadays the constellation data is available on the open source. Okay, so we take observation data, direct you take IRI model. Here there no need to derive any derivations in IRI to those IRI models, because direct from online you can take the TEC values. Suppose if you take huge amount of, suppose if you want huge amount of data, then you can write one simple Python program how to retrieve the data from web model. So there is a lot of scope is there for the research by using these models. So next IRI PLAS 2017 model. This is also one type of IRI model only. The difference between that model and this model is IRI model, it can predict the TEC value up to 0 to 2000 kilometers only. So IRI PLAS 2017 model about 2000 kilometers, from 2000 kilometers to 20,200 kilometers, because GPS signals are coming from that height only, 20,002 kilometers. So few studies, literature says that some plasmaspheric part contribution is also there in the contribution of this ionospheric delay. Not only up to 2000 kilometers, about 2000 kilometers, sometimes because of the storms, some TEC contribution is there. So we need to consider that part also. Then they initiated. So extend the model to up to 20,200 kilometers. So using this model also, the same data, observation data we used for this model also, we validated. So direct, I will show you the results. This is the flow, how we are follow the steps to get that analysis. And in this we use IRI model, IRI plus 2017 model, IRI plus 2017 with the assimilation of TEC input. Because IRI plus 2017 model it did not provide the good result. So that's why we assimilated external TEC input into the model. Then it shows the good result. So completely, and GIM TEC also we used. So completely by using complete data, we developed one GUI also for complete 2017 year. So this is for statistical analysis only, difference one, different two, different three. So these are the plots, IRI plus with TEC input, GIM, IRI plus with no TEC input, IRI 2016, and NAVIC TEC for quiet days. This is for 12 months, quiet days, 4 models. This is for disturbed days and the seasonal variations for quiet days, disturbed days. So, and this one is error, percentage of error. So how much the model is deviated with the observation data. For every model we calculated. So you take here IRI plus with TEC input with the NAVIC. Between these two model, with these two, we calculated the percentage of error. You can see, I will explain only for 1 month only. If you consider January month, so here the blue color is IRI plus with TEC input and NAVIC data. The percentage of error is showing less. When we are comparing IRI plus with no TEC input, the green color, so it is showing the much error, 50% of error is there. So it is not giving that much of accurate results compared to with assimilation. And pink color is IRI 2016. So it is from 0 to in between 15, but it is varying from hour to hour also. But peak hours, afternoon hours, the deviation is more. This red color global ionospheric maps, this is from IGS networks, they collected the data. So that's why it is error is almost closer to 0 because it is real-time data. Actually, it is from IGS network stations. So this is the procedure how to validate the models by taking the error, percentage of error. Means it is underestimated or overestimated or it is following. These things we are saying. This is for quiet days and different disturbed days. For instant and quiet days, highest monthly and seasonal error deviation of about 130, 89. In December and March equinox months, we observe that one for quiet days. Disturbed days, 100%, 77.24% are observed in December and June months. So, advantage of assimilation technique. When IRI plus is assimilated with the GIM TEC, the resultant TEC is closer to the NAVIC data and percentage of error is around less than plus or minus 15% only compared to other models which are showing large deviations. Other models are showing large deviations. When we are assimilating TEC, GIM TEC into class model, it is giving better results compared to others. And this is mean and RMSE values. And the difference between difference means between the models. I will explain direct this table. Model 1, model 2. Suppose if you take only these two models, IRI plus model with assimilation, IRI plus 2017 model. So improvement of assimilation over model 2 is 88 point improved. So that is the advantage of assimilation. 88% of improvement in November we observed. For disturbed days, 90.57% observed. And this model over IRI 2016 model, 79% of improvement and 77 improvement in October for disturbed days. If you compare only IRI 2016 and IRI plus 2017, here improvement is 70, here improvement is 70.48%. This is for monthly percentage, highest percentage improvement. This is seasonal highest percentage improvement. So your overall conclusion is compared to IRI IRI 2016, IRI 2017 models. IRI 2016 is better than IRI plus 2017. But when we are assimilating TEC into IRI plus 2017, it is giving better results. And one point I can say, all these models, this analysis only for that particular year only. I am saying 2017. Maybe if you take one more year, any other solar activity year, maybe these results becomes different. Maybe at that time, PLAS model will give better results than IRI 2016 model. So this model, any model, does not provide the fixed result to that particular station or year. So it's changing from year to year or station to station. That's why I'm saying there is a lot of scope for the research in the ionosphere. You take any year, any station across the globe, number of IGS stations are there. The data is freely available on the website. You take just GPS data, you collect 5 station data for 5 years, then it is easy to publish science citation index papers. And one publication, Advances in Space Research journal is there. It is very standard journal in the GNSS ionospheric studies. So that journal, they are looking for a huge amount of data. Then they will accept the paper because they are showing for a result. So for many years data. So that's why the scope is high for this ionospheric studies using all these models. We have plenty of models. You take any two, not only to develop a new model. For existing models also, we can do a lot of research. This is only for research point of view, not real-time application. For ionospheric studies only. Sir, is there any time limit, sir? Yeah, okay, I will close. Yeah, okay, sir, I will close. So we developed one GUI using all the data, whatever the data we analyzed.
Madam, please take for another 10 minutes, madam.
Okay, sir. Only one more model is there, sir. Two model.
Please continue, madam. Continue.
Yeah. So far we discussed IRI PLAS model, IRI 2016 model. One more model, NEQUIC 2 model is there. Again in NEQUIC there are two models. NEQUIC 2 is there, NEQUIC G is there. NEQUIC G used in Galileo receivers, that is a mathematical model. It depends on coefficients A0, A1, A2 ionization levels. So that is different part that is used in real-time receivers. NEQUIC 2 model is a web model. We can predict the TEC from this ICTP website. So this is research point of view. We can use this model to validate the ionosphere contributions. It is developed by ICTP. I will show you these websites also how to extract TEC from the models if time permits. So simple, NEQUIC model also, it can predict the TEC about 2000 kilometer also. In our analysis, we used NAVIC satellites 36,000 kilometers. So here you can say 0 to 1000 kilometers, 1000 to 2000 kilometers, 2000 to 36,000 kilometers. So in our analysis for every NAVIC satellites, we calculated TEC from mean sea level, means 500 meters to 36,000 kilometers. So this is the flow of methodology, how we are following the steps to get the result. See here, for all satellites, first graph only mean 0.498 kilometer means 500 meters, mean sea level. 500 meter to 1000 kilometer, the TEC contribution, STEC, first we calculated STEC. Because here we are using in NEQUIC model, it needs satellite elevation, azimuthal angle, ray ending point. Here I am show ray ending point, starting point. So that's why first we calculated STEC. After that, by substituting that corresponding elevation angle of the satellite, we converted to VTEC also. So here we found from the result, here from mean sea level to 1000 kilometer, the maximum TEC, 80 TEC. Again, I calculated from 1000 to 2000 only. So what is the contribution above 1000 kilometer? I tested. So then the TEC is there actually. That is from, if you observe for all NAVIC IRNSS satellites, the TEC value 3 TECU is there. So, but the part is very less, but even TEC contribution, this is only for low solar activity. Maybe for other years, that contribution may be big. So like that we tested 1000 to 2000, and this one 2000 kilometer to respective satellite height. So almost these two graphs are same, because above 2000 kilometers, there is maybe only small contribution is there. And the fourth one is 500 to respect to satellite height. difference. So from 0 to 2000 and from 0 to complete satellite height. So this is the difference we observed about 2000 kilometers. So for 1B satellite 1.5 TECU, for 1C satellite 2 TECU, D like that. This analysis done only for Navig. We can do this analysis for other constellation also. We make one paper with the result like that. So like that for all satellites we calculated TEC above 2000 kilometer. So this is the contour plot. From this, the advantage of this plot is we can say by seeing this graph, the contribution is highest for during which period we can say by seeing this graph. So in this period, the yellow color from some 6 UTC to 12 UTC, this distribution is more for all PRNs, all satellites. So that is the advantage of contour plots. So this is simple plots for all satellites month-wise we plotted. The analysis of
Madam, last 1 minute.
Yeah, okay, sir. So this is complete statistical analysis and this one. Okay. So compared to in our analysis, we found that compared to IRI 2016 model, IRL plus model, NICVIC 2 model give better results compared to those two models. We observed that thing. So, and recently, actually, we used IRI 2016 model only. So recently, I found this paper. This is very excellent paper. So, in this paper, just August 2025, they published this paper. Performance analysis of NICVIC 2, IRI 2020 and IRI 2016 ionospheric models over equatorial low latitude and high latitude regions during the descending phase of solar cycle 23. We consider 11th solar cycle. In this paper, they considered descending phase of solar cycle, that is 2008 year data. So in 2025, they published using 2008 data. So that is the beauty of this research actually, ionospheric. You can take any year. This is this paper published in Advances in Space Research. Actually, these authors attended the seminar at CASPAR IRI workshop and they published the paper. So here in this paper, they consider three models, three different stations, equatorial. They consider Antarctica and Lucknow, Delhi stations, low latitude, high latitude, equatorial, and 1 year only, 2000 year only, they observed by taking quiet days, disturbed days, most quiet days, most disturbed days with GPS data. They validated the performance of these three models with GPS data. They found that these models are following observation data for low and equatorial stations, but the significant improvement is not there for high latitude region they found. So and many things are there, but just I am giving the idea. This is the thing you can publish because there is nothing to develop a mathematical model here. Just you extract the TEC from these online models. These are direct available in the website models. IRI site, IRI and NICVIC ICTP site, if you open direct to TEC, we can extract. Observation data is also available in the website. Just you validate and you give the points. What is the ionospheric contribution in that particular region or in that particular year? That is the new thing we found. We are testing the model validation. These inputs are very useful to IRI team because they will update accordingly. They will take the inputs from our publications and symposiums, workshops, and they will update the models. So that is a great achievement for us for in this area, I can say. So okay, thank you, sir.
Thank you, madam. Participants, any queries, any questions, please ask.
If time permits, I will show you the models, online models also, sir. If it permits, otherwise leave it.
You please share the PPT, madam. I will share with the
If anybody are willing to do research in this area, sir, please contact me. I will help them. We can do the work for huge by taking huge amount of data to validate all these web models.
Okay, sure, madam. Thank you. Thank you.
Okay, sir.
Now it's the time to propose vote of thanks. I request the Preeti Elizabeth to give the vote of thanks.
Thank you, sir. A very good afternoon to everyone present here. On behalf of the organizing committee, I take this opportunity to express my heartfelt gratitude to all who contributed to the success of today's session on performance evaluation of global ionospheric models. First and foremost, I extend my sincere thanks to our chief guest, Dr. Kavitha Devireddy ma'am, for sharing valuable insights on ionospheric behavior, modeling changes, and the comparative performance of global ionospheric models. Your expertise has greatly enriched our understanding of this dynamic and vital domain, especially for applications in GNSS satellite communication. I also wish to thank our management, secretary sir, principal sir, head R&D, HOD ma'am, faculty members. Finally, I thank each one of you for your presence and cooperation. Your support encourages us to continue organizing such academically enriching programs. Once again, I thank you, Dr. Kavitha ma'am, and thank you all. Have a great day.
Thank you. Good evening all. Our next resource person has joined. Now I request Dr. B. Divya to introduce the chief guest.
Good afternoon to one and all. I'm happy to introduce the speaker of today's session, Dr. Punyawi Jamjareegulgarn, Associate Professor, the head of the Space Technology Development Center at King's Mongkut Institute of Technology, Ladkrabang, Prince of Champagne campus. He holds a Doctor of Engineering in Electrical Engineering with a specialization in Earth and Space Technology from KMITL. His research spans AI and machine learning for wireless communication, wireless sensor system, IoT applications, climate change, disaster research, and aerospace engineering. He also delivers keynote work on space weather and GNSS-based research with the collaborative efforts across the Thailand and Asian countries. He has published several papers in high-impact journals and having a H index of 18 and I-10 index of 26. We welcome you, sir, and I have a hand over the session, sir.
Yeah, thank you very much. The executives and lecturers of this conference program. Yeah, I'm very pleased to share our knowledge to you about the plasma bubble. Can you see my slide? Hello?
Yes, sir. Yes, sir. It is visible.
Yes. Can you hear me well?
Yes, sir. Yes, sir.
Yeah. Thank you. I'm not sure that it's a full screen, right? Okay. I'm really pleased to talk about the plasma bubbles and ionosonde measurement. I'm really grateful for the previous lecturer. Some contents will be duplicated from my slide as well, but I will try to describe you in details with the many equations in many models, okay, related to the ionosphere. It is a very good have many interesting topics about the ionosphere. I hope you can enjoy and get a lot of the experience. Okay. My topics, I want to talk about the ionosphere and ionosonde and the next ionospheric parameters and its magnifics, IRI and equal models, how you can apply these global models to your research. And then I will invite you to travel to the DID base and Kilo websites, introduce you about the instruments at the KMITL Chumpon Station, Thailand, talk about the ionospheric disturbance, recent EPB researches and control room activities of my university. These two figures are Ionosonde and GNSS at my Chumpon campus. Okay, the first, as I think that as you know, it's well known that the ionosphere is the main atmospheric layer. It occurs the recombination and photoionization layer during the length from the 50 to the 2000 kilometers approximately. It is divided into three layers: D layers, E layers, and F layers, as shown on the left panel. During the daytimes, okay, F layers is split into the two sub-layer, F1 layer and F2 layer. In contrast, in the nighttime, without the sunshine, F layer can show you only the single layer, okay, compared to the day side. Okay, so electron density is the highest in the F2 layer region. So F2 layer is the main layer, reflects the HF signal from 3 to the 30 megahertz. And F2 layer also effects on the propagation delay time of the satellite signals. Okay. Okay. If you see on the left panel, okay, it is the electron density profile of the period at the Chumpon. I will show you how you can see the electron density trace, and everyone should see that we have the many main parameters. Okay, the first one is the maximum. I mean the peak density at the F2 layer, namely in F2 at the peak height of the F2 layer, namely HMF2, and two main parameters. Okay, I am the specialist of the B0. B0 is the bottom side thickness parameter, and H2 is the top side thickness parameter. We combine B0 plus the H0. It is the slab thickness. That means it is something like a density of the F2 layer. When you want to calculate the slab thickness, it is equal to the ratio between the TEC and F2, as mentioned by the earlier researcher, that TEC is the integration of the electron density from the satellites to the GNSS receiver. So you can see that they combine the whole electron density of the whole part, okay, of the atmosphere around the HMF2. Okay, so here you can see the tech U, right? The tech U is equal to the 10 power 16 number of electrons per square meter. And you can calculate as well the ionospheric delay, okay, based on the frequency use of the GNSS frequency, okay, and then you can get the ionospheric delay. So our previous scientists and physicists, okay, scientists, they're really smart. They calculate because we can apply the TEC, okay, to calculate the atmospheric delay. It main, I mean the main effect, the navigation system. Okay, I will show to you about the ionosonde. Okay, the main elements. It is used to measure ionospheric irregularities. Ionosonde is the radar in the World War II. Okay, after the war, okay, ionosonde is used for monitoring the ionosphere at the HF frequency. Okay, you can see the concept of the ionosonde is I mean radiate, transmit the RF signal to the sky. Okay, when they I mean touch to the electron density in the space, and then they reflect back to the receiver. Okay, and then the frequency is up to every the 100 kilohertz per second. The frequency is up until it cannot get the reflect back the signal. So we call the maximum frequency or critical frequency at the F2 layer, namely the FOF2, okay, frequency. And then when the RF signals echo reflected back, it will record as the ionogram in the computer. So you can see the ionogram trace in the computer on the screen. Okay, here only introduce you that we have the blue green line as the primary trace, and the yellow is the secondary trace. Okay, these are the examples of the parameters. Okay. Um, I am in Thailand, so I use the FMCW Ionosonde since the 2003. This Ionosonde is one of the 8 sea lion ionosphere where I used to monitor the ionospheric variation over the Asia Pacific near the magnetic equator. And then you can see that nowadays digital zones are mainly used at the several stations throughout the world to draw the ionograms and provide atmospheric parameter automatically. Yeah, you can see this figure that you can see the two parallel lines vertically that these are is why is about the 140 kilometers around the 100-degree east to capture the atmospheric variation, okay, between northern and southern hemisphere, okay, around the magnetic equator. Okay, this table show you the operation parameter of this ionosonde. Okay. I will show you, as mentioned earlier, that there are many parameters, some main parameters. For example, the critical frequency of the E layer, critical frequency of the F2 layer, virtual height of the F layer, and maximum usable frequency at 3 kilometers distance of the F2 layer, and so on, are provided by this ionosonde, right? And then NF2 and HMF2 are only compute using those scale ionosonde data. You can see that if you use the ionosonde, you should scale manually the atmospheric parameters. It's not automatically scaling. And then in AF2 and HMF2, you must use the empirical formula as shown below. Okay. If you see the diagram, I just described you. This HMF2 is the my previous study. Okay, it is the another formula to calculate the HMF2 that you can meet it, find it in many papers. Okay. It is just only the one example. Okay. You can see you should find the correction factor delta M, okay, and use the propagation factor M3000 F2 in this equation, and then you can get the HMF2 in unit kilometer. Unfortunately, that B0, S0, TC, and electron density values are not provided on the ionosonde as well. That's why if you want to use the ionosonde, these 4 parameters cannot find. Okay, I show you here. You will, if you have available time, you can calculate. Follow me, okay, by these 3 examples. Okay, benefits of the ionospheric parameters. Okay, the first, you can use them to calculate the electron density, follow to the IRI model equation or NEQUIC 2 model. Okay, and its impact on the total electron content and satellite delays as mentioned earlier. Okay. and you can computing the accurate position for the GNSS and GPS system and so on, investigating the impacts of the space weather on navigation, agriculture, disaster, etc. Investigating the peculiar events such as the plasma bubble, okay, equatorial ionization anomaly or EIA. This is the next issues. I want to tell you about the global empirical model, okay, namely IRI model. IRI stands for the International Reference Ionosphere. Mainly, IRI focus on the bottom side electron density profile, okay? Everyone must know this well-known equation, okay? You can calculate the electron density with respect to H, okay? It is in the form of the HMF2 and multiply with the exponential minus x power b1 and hyperbolic cos x, okay? Here, B0 is the bottom side thickness parameter and B1 bottom side shape parameter. You can see in this figure, okay, in this figure, if the F1 exists, okay, you can use the HMF2 minus the HMF1 equal to B0. But in contrast, if the F1 is not exist, okay, does not exist. So B0 can calculate from the HMF2 minus the H0.24. You know that H0.24 is the main, is the main actor, okay? It means that IRI consider when the electron density decrease left over to the 24% of the HMF2, that means it's something like an entry point. So it might just minus the H0.24. Okay, you can get the B0 at the bottom side. Okay, this is the main idea of the B0. Okay, but you can see that IRI model didn't show you about the S0, right? As I mentioned earlier, you can see the H0 from the N equal to model. Yeah, is the main research when I study the doctor program at the Ladkrabang, Thailand. Okay, the second model is the N equal to model. An equal to model is another ionospheric model and use the bottom side thickness parameter as well, but it used another notation, namely the B2 bot. Okay, so when I study the doctor, okay, I face to the problem, okay, because B2 bot seems to be analogous to the B0 of the IRI, but it seems the same thing, but the different approach to find it, okay? So how you can show that B0 and B2 bot seems to be similarity, okay? So I try to follow, study the B2 bot from paper Gonzalez and Lidisula, okay? They use the Ionosonde data, okay? You can see B2 bot is calculated from the NNF2 at the maximum derivative between the electron density respect to H. It seems to be the numerator, it seems to be the entry point to calculate the B2 bot. Okay, you can follow its idea from this paper. Okay, it's the first important paper. Yeah, I try to argue this equation that because I want to propose the new idea, you know. So I read it and I know that 0.3x5 is needed to update by Wang in the 2010. Can it be used directly for Chumphon station? Because as mentioned earlier, that Chumphon has only the Ionosonde, right? Ionosonde does not exist the zero. So how you can know? And which equation and device can be used to calculate, okay, the B2 bot apart from the ionosonde. This is the main point. Okay, before I skip to the next slide, I'm not sure that the lecturer told you earlier yet about that B0 of the IRI. There are three kinds of the B0. Okay, the first one original is the B0 of the Belisa. Okay, and B0 Gruyewa and B0 ABT. Okay, and then I study to retrieve the B0 observed from website of the Nitizen. Okay, I will show you it later. Okay, this is my compare the figures. Okay, and this is show you how to can calculate the B2 bot following to the NUX2 model as mentioned the previous slide. Okay, it's really easy. You can I show you here, and I hope you enjoy to calculate as well, because my previous colleagues had to plot this equation as well. Okay, and if I want to try to propose the new equation, I propose B2 bot propose. Okay, I start from the Professor Zhang from CAS Chinese. Okay, Chinese guy. I use TC from this equation. You can see it is directly relationship between the TEC and the B2 bot, right? The main actor, again, the main actor is K. K is the relationship that they're scaling from the HFF2, FOF2, and the RC12. Okay, and then I rearrange following to the Professor Zhang. Okay, I met her in Thailand as well. It's really good time, good chance to talk with her about her equation. Okay, and then I calculate, propose, rearrange, and I get the new rearranged equation as shown you in this figure. As mentioned you earlier, right? Tau is the slab thickness, HMF2, and then L. L, you can see L didn't show you here, but if you see KL is the many terms, right? After you rearrange the original K here, very simple. Okay, you can see in my paper, yeah, this the 14th slide is this my paper published in the Advanced Space Research. It's really easy. When I published this paper, yeah, the reviewers asked me that how you know your equation can be used in any equipments or any standard. Okay, I'm encounter the problem. I really sad how I prove that my equation is correct or can be recognized to be used in worldwide, right? But fortunately that after I use the parameters from the kilo, okay, I I will find that it seems to follow well to the observed B0. You can see compare with the standard IRI B0 ABT. That's why I graduated. This is the first main paper to nearly finish from my PhD program. Okay, you can follow my paper. Um, I talked tell you the truth. I can only compare to the B0 ABT because it is the main. I mean, it is a good B0 figures that follow well to the observed B0. Okay, I didn't compare to the B0 Guruyewa and B0 Bilisa. That's why I finished this paper. Okay. As mentioned in earlier that during this paper, the IRI show us only the IRI 2012 models and NQuick 2 model during the solar cycle 23 okay cycle. That's why I try to follow at this solar cycle. Okay, I will show you how you can get the ionospheric parameters from the Nitizen. I'm not sure uh, you know from the previous lecturers or not, okay? But I invite you to go to the DID base, okay? DID base, I show you here. Okay. You can see the station list. Okay, there are more than the 1,100 stations in the station list. As you can see from the DID maps, they located many DT zones throughout the world, and you can see the calendar list. Okay, okay, this one is a fast station list. Okay, when you want to study many station name, okay, invite you to use the URSI name, and please go to put many copyright statements to recognize the data you use in your paper, okay, correctly. Regarding to the DID based website condition, okay? And these are the geographic latitude and longitude. For example, Ascension Islands, right? You can see it at the southern hemisphere in the west of our countries. Here, the above one is the list of year for Guam, okay? You can see many years, and then deeply go in depth. You can see many months of the Leo that ionogram from this Nitisan station of Guam in the 2014. Okay. This one is the DOY, right? Day of year, okay? Follow the day of year. It introduce you the shortly how you can find the many existence of the database, okay? When I want to show you another scale, the ionogram, I always use it as well. Yeah, really easy. Yeah, you can put the select time interval on the left panel, start and stop, and then you choose many parameters you want to study, and then you can choose in at the two. Okay, number two, you can choose the kilo location. For here is a Guam, okay, and then you you enter so you can you can get the data, okay, at the kilo. They mention you that when you retrieve your data from your interesting station, okay, and then they tell you about the Ionosonde model they use. Uh, Fortunately, that the more than the 100 stations of the Digizone, some station notated from the Lowell, and some countries they have some money, right? They can buy to install the Digizone, and then they participate in the Lowell database, okay, of the USA. So here I show you the only the HMF2. The main point is that when you retrieve from the HMF2, okay, there may be some the not a number, or they didn't exist some data during your desired date. Okay, that means when you it very necessary to clean pre-processing your I mean your real data first before using it. Okay, in practice. Okay, the next topics I want to show you talk about the KMITL Chumpon Observatory Station. As mentioned earlier, that Sea Lion project. Sea Lion is the shortened word, okay, from NICT, and supported by some country in Southeast Asia since the 2003. It is the ionospheric observation network in Southeast Asia around the 100° east. As mentioned earlier, that about the 140 kilometers, right? And conjugate observation stations were also implemented in the northern and southern hemisphere around the magnetic equator. You will see that why you should have the both hemisphere, because some peculiar, I mean some disturbance will occur and move up and down. Okay, you can see the peculiar events. Okay, Ionosondes have been installed 5 phases over the Southeast Asia region in 4 countries. In Thailand, we have the Chumpon. Okay, you can see my mouse over them, Chumpon and Chiang Mai. Okay, and then Indonesia, Philippines, and Vietnam. Okay, Indonesia we call the Koto Tabang. Okay, Philippines we call the Cebu, and Vietnam we call the Bạc Liêu. Okay, and you can see 3 more stations are located in Japan. Okay, Kochubanchi something. Yeah, I forgot it. Okay, to monitor equatorial ionospheric disturbance and equatorial plasma bubble that influence directly on the HF communication and GNSS. Okay, in this slide, okay, very fortunately that you can see the first one is the ionosonde. The second one, VHF radar at the Chumpon station only. Or sky imager, okay, or sky imager, we have many places, okay, at the Chiang Mai, okay, Chiang Mai and Chumpon. And GNSS receiver, okay, many places as well. And magnetometer, okay, Phuket, okay. Here, show you the figures of my ionosonde at Chumpon, and this is an ionogram, and this is a ionogram that you should scaling by manual. Okay, and you always try to scale the plasma bubble, plasma frequency at the F2 layer, and H palm F is a virtual height of the F layer. These two H palm F, we always often use it to study the period events of the ionosphere because it's something like the rising up of the F layer. You will the researchers always use the virtual height to study from the ionosonde. Okay, and the second instrument is the GNSS receivers. We have many receivers by the various institutes. The first one in ICT, JAXA, CAS, Kyoto University, and KMITL. There are many receivers figures, but I didn't show you all kinds of the GNSS receiver here. But the mainly I want to show you that what is the main point of the TEC, because we always use the TEC rate of change of the TEC change from the STEC. STEC is the slant TEC, right? And then after that, we use the zenith angle and the upline to calculate upline factors to calculate the vertical TEC. And then if you get the lot, right, we calculate the ROTI or ROT, okay, from the average of the lot square and the average square, okay, from this equation. You can find the lot and ROT equations by many papers, okay, in the literatures by yourself, okay. This is my famous equipment in Chumpon. Sorry, we just get the model, the modern VHF radar from the NICT. Okay, we use ask for the frequency permission from the Sawyer and the Thailand organization. Its operational frequency is the 39.65 megahertz. Okay, and we use the 18 Yakis Pana array okay, and it gains about the 22 isotopic decibel. It lends to detect the equivalent plasma bubble between 140 to the 55.2 kilometers. It noticed from the NICT, okay, when the VHF radar they transmit the HF frequency into the sky, okay, they will reflect back and capture it, store as the quick look images as shown you in these figures. Okay, we can see that from the length, okay, from the length is mean the height of this plasma bubble, okay, with respect to the frequency. Okay, as shown you earlier that VHF radar, okay, it just located and has been used at the Chumphon since the 2012, 2020, okay, and previously we also has the Ionosonde and the GNSS receiver. Uh, as for the northern hemisphere at the Chiang Mai, okay, you can see we also have the Ionosonde GPS and all-sky imagers. Right now, Chumphon also has an all-sky imager. On the other hand, you can see at the Koto Tabang, they previous have the many equipment as well. Okay, especially you can see the Ionosonde GNS receiver and two main equipments. Okay, two main equipment is the ear. Okay, Equatorial Atmosphere Radar donated by the Kyoto University and VHF radar from the Nagoya University and all-sky imager Fairy Pilot interferometer from the Nagoya University. The main point is that they want to capture when I will show you later that plasma bubble or the electron density irregularities often occurs at the magnitude equator, okay, and then they spread in elongation along the magnetic field, spread out, okay, spread out to the higher latitudes. That was they will occur at the Chumphon first, and then they spread, okay, I mean travel to both to the north and south, okay, they will capture it later, okay, as shown you in these figures. Okay, um, the next topic, okay, I will focus on the ionospheric disturbance, or you can call it the ionospheric irregularities. I will show you the four main disturbance in the ionosphere. It's very interesting. You can make your research now. Right now, I didn't explain you more, but hopefully that if you can read more details. Okay, the first one is equatorial ionization anomaly or EIA. Okay, and you see that EIA something like a dot at the magnetic equator, and you can see the curves uh, at about the plus and minus the 15 to 12 degree, okay, along the magnetic equator. It seems to be the last plasma density of the EIA curves causes by increase the group delay of the GNS receiver, GNSS signal, leading to the errors in positioning and navigation position. The daytime upward plasma dip due to the E-layer dynamo, okay, is responsible for the development of the EIA, okay, that maintains the maximum intensity at the curves during the daytime, okay, and many papers always study about the EIA enhancement. They found that EIA enhancement is also associated to the strong eastward E field and thicker to the main phase of the geomagnetic storm during the day side. Okay, you can study from my this paper. They will show you how EIA they can get effects during the geomagnetic storm. Okay, and this you can see on the light panel if you use the light hand, right? Something like E is the something like the eastward electric field, and then B is the magnetic field is moving from the south to west. Sorry, south to north, right? And you can find the vertical E cos B dip, okay, upward, upside, okay? And then when something like energy, when they move up, right? When the energy is down, it's nearly to out, right? It's spread out, elongation with the magnetic field, okay? So that why you can see like, okay, like this one, okay, like this figure. Okay. B, I will show you that the scintillations, okay? Scintillations are rapid and temporal fluctuations in amplitude and phase of the radio signals. It also resulting from the electron density irregularities. Here, EIA is also responsible for the plasma density irregularities that give rise to the scintillations. Okay, so in general, as mentioned in my paper as well. Okay, you can follow me these papers below. Okay, scintillation is believed to influenced by the local time, season, solar activities, geomagnetic conditions. Okay, and so on. Okay, and you can see coronal mass injection and solar wind, okay, during the solar flare, okay, will also interact with the ionosphere, can cause the severe irregularities and thus the scintillations, and then it will lead to the equatorial plasma bubble as well. So if you start to study, right, there are many causes that lead to the irregularities. That means you have a chance. If you have many possible the instrument to study and detect well the new phenomena, that means you can publish your research. Okay. The third events, we talk about the equatorial spread F. Yeah, it also from my laboratory, okay, at the Chumphon station. You can study from this paper, this below paper as well. Okay, what is the equatorial spread F? Okay, it is the nighttime irregularities, okay, events. They always occur at the bottom side, equatorial ionosphere. ESF, we have like a scattering of the equatorial F layer trace in the diagram at the nighttime near the magnetic equator. It's something like you cannot receive the signal well. You cannot read, okay, because the signal spread out, okay, something diffract, so it cannot communicate it during at that time, okay. ESF, okay, can have various space size between a few centimeters and hundreds of kilometers with respect to the frequency band and height, okay. And also plasma instability is caused by uplifting, okay. You can see the uplifting again, uplifting of the bottom side F region plasma gradient, and we call the Rayleigh-Taylor instability process or RTI. Listen, you can see that during the nighttime, why it occurs many peculiar ionospheric events, because we have no sun. So the D and E layer, they occur the faster recombination compared with the F layer. So you can see they will occur the electron density gradients easily. When something like there you can see the electron density gradient, right? That means you can get in touch with many peculiar events at that time. Okay, that's why many nighttime you can see many events, many steadily. Okay, ESF the plasma. Oh, sorry. ESF and plasma bubble is also driven by the evening P-reversal enhancement again. We call the PRE. That cause the sudden uplift, okay, of the equatorial F layer. And ESF occurrence lead to the instability growth at the bottom side, okay? So-called the plasma bubble events. Okay, I invite you to study the spread F prediction model from our labs. Okay, right now IRI model also try to calculate the spread F probability as well. Okay, this very new issues for the spread F prediction. Okay, this is our main actors, right? The fourth is equatorial plasma bubble or EPB. It's something like a flux tubes aligned vertically. It is caused by the plasma depletions rapidly, and then they elongated along the geometric fuse lines, as I mentioned earlier. Its scale size range from tens of centimeters to 100 of the kilometer. EPB typically originate at the bottom side of the F layer after the sunset, as I tell you that, right? And then often move from west to east, like directions of the solar wind and PRE. You can see, and it leads to the ionospheric delay gradient and scintillations impact directly on the GNSS navigation and HF communications. Okay, I invite you to study my paper. Okay, they will talk about the solar wind. Okay, and how these two main phenomena can cause the EPB during the nighttime, okay, especially at the post-sunset and midnight, okay, and sometimes it will lead to the early morning as well. This is my recent EPB research, okay, at my Indian guys, okay, Panda, okay, and co-authors. We just published in this year, okay. And I focus on an seasonal development of the post-sunset EPB over the East and Southeast Asia using many instruments, okay. And the results indicated that the formation of EPB are primarily driven by the southward orientation BZ in storm main phase, okay, which caused the penetration of the eastward electric fields into the equatorial ionosphere. You can see that during these 2 years, 2024 and 2025, we are at the solar maximum of the 25th, okay, solar cycle. So that why we can find many strong geomagnetic storms and many interesting researches occur during these 2 years. Okay, our findings emphasize the need for continuous regional monitor of the plasma bubble to mitigate the space weather that impacts on the satellites and GNSS. Oh, this is the second research. Okay. We cooperate with the OCO at the Nigeria. We use the bootstrapping convolutional neural network technique to detect the equatorial plasma bubble on the Oscar image. Okay. Uh, we we use the CNN trainings on the sub-data sets of the three images for each category, namely EPB, noisy or cloudy, or no EPB. Here, noisy or cloudy, that means it's really chaos. You didn't classify whether EPB occurs or not. Okay, and no EPB. I want to share you something. I just get from some specialists from the image processing. They 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 wi- they told me that maybe if you get the noisy or cloudy on your Oscar imager image, right? Maybe it's something like a acoustic sound frequency. So when you want to filter Oscar imager, you should check that something like occur during your measurement or not. Okay, maybe it's occur from the many, interference signals. For example, the acoustic or sound waves. It makes you disturb your instruments frequency. Ensemble models, okay, sorry, occur. Our results indicated that bootstrapping CNN can be detect the EPB detection accuracy, providing a powerful tool for the real-time space weather monitoring application. And my third research about the EPB, I also use the convolution neural network and support vector machine as to detect the occurrence of plasma bubble of the VHF radar at the Chumphon station. Okay, we only use the 500 image for each class of the EPB, unsure and noisy EPB as well. Okay, and we get the accuracy more than the 92%. Okay, you can see more details in this paper. They just published in 2 years ago. Okay, that now machine learning and artificial AI always apply to the space weather. Like now in our space community, especially COSPA or IRI and EQUIC, or many space conference, they recognize that my previous elderly recognize that AI and machine learning tools can be used in our practice already. So you can but try to convince us that it really useful and it can be used directly. Okay, possible in our studies. Okay. Ah, Oh, sorry. This is the research, EPB research for. Okay, sorry. Um, we study about the ionosphere delay gradient estimation project. Okay, as the many Europe papers, we should set the experimental test bed. We have the three station. Here I start at the KMITL. And then we have two beds lie between the Stanford University. The first one, its length is distance is the 12 kilometer and the 4 kilometers between the Suvarnabhumi airport and KMI University because we act like it will recognize that the plasma bubble will affect directly on the GBAS. GBAS is the cloud-based augmentation system to airplane landing. Okay, we try to measure and detect the how the airplane can land exactly accurate. Okay, on the path directly during the geometric storm or during the plasma bubble. Okay. if you study about the GBAS, okay, two main parameters that you should consider is the delay gradients and protection limits. Okay, because protection limit that means during if your airplane is landing, right, it should be get the accurate position within the position limit only. If higher is something like an alarm, it will very dangerous because it's not detect the accurate the position to land. Okay, and if the so that's why if we want to calculate the ionosphere delay gradient, we also calculate the scintillations because it's something a loss of log the signal. Okay, and during the plasma bubble and the intense the scintillations. Okay, here we focus on the 4 seasons. Okay, during the quiet times and disturbed time as well during very to 2011 and 2012. Okay, between these two baselines, and you can follow and the atmospheric delay gradients, and we have very high delay gradients is reached to the 80 millimeters per kilometer. Okay, at the at the plasma bubble. Okay, I show you in the figure. It's published in the IEEE Access. Okay. This is my control room. Because not only the I open the control room of the CEG, we call the Center of Excellence in GNSS and Space Weather at the KMITL Bangkok, Thailand, led my supervisor, Professor Dr. Ponchai Sapniti. Okay, this my laboratories at the Bangkok, Thailand. Okay, and we try to open the control room as well at my Chumphon campus. Okay, I hope to be settled it recently, but it's really hard because um, we 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 have no leftover rooms for settle the control room right now. Okay, this is my summary. Okay, lots of the space weather, climate change, and disaster researchers are conducting ongoing amongst my institute and neighboring partners. Our main focuses are still on the atmospheric irregularities investigation, space weather forecasting, plasma bubble, climate change, and disaster. Our ongoing study requires several eager and smart researchers as well as the collaboration among various countries. Okay. Um, Follow to this slide summary, I want to add something, okay? Because if you I start from the bottom side thickness parameter or B0 from the ionosphere monitoring, right? And then I move to the GNSS receiver to retrieve the TEC. And then it's really important that TEC from the GNSS receivers can be used to measure many things, okay? For example, the space weather and can be used to detect the earthquake disaster, okay? And you can calculate the precipitation we use to predict the climate change as well. So that's why right now I didn't show you here because um, I want to talk about the ionosphere measurement, right? Ionosphere measurement and plasma bubble only. But you can study my researches from my Google Scholar, okay? As I post you in this chat previously by the end of previous lecturers, and so you can see many climate change. For example, the flash flood, the soil erosion, okay, and the ocean or sea rise sea level rise. Okay, that means they can make you the flood. Okay, on your land. Okay, and many disaster, for example, the earthquake. Okay, okay, this. No, that's all my presentations. Okay, thank you very much. Thank you for your listening. Okay, you have any questions?
Thank you, sir. Participants, any questions are there? Please ask.
Yeah, you can hear me well, right? Okay, thank you.
I think no questions from the participants, sir. So I request Dr. B. Divya to propose the vote of thanks.
It is my distinct honor and privilege to propose a vote of thanks for the today's session. First and foremost, a huge thank you to our esteemed speaker, Dr. Punyawi Jamjareegulgarn, for gracing us with your presence and for your incredible insight presentation. I'm sure everyone here left feeling much more informed and inspired. My sincere gratitude also goes to our respected Secretary Sir, Principal Sir, Head R&D and Head of the Department for their continuous support in organizing such a continuous learning opportunities. To the organizing committee, volunteers, and our dedicated faculty, thank you for your tireless efforts in ensuring this event ran so smoothly. And finally, thank you to our wonderful audience for your enthusiastic participation and thoughtful questions, which truly enriched the discussion. We truly gratitude for your time and wisdom, sir. We look forward to welcome you again in the future, and thank you all.
Yeah. Thank you so much. Let me introduce you again. I didn't show you many the simulation or explanatory result. Okay, I invite all of you to go to study about my research. Okay, for my Google Scholar link, and then welcome you all to ask me more. Okay, if you have any questions. Okay, thank you very much. Take care, all of you. Okay, see you. Thank you very much. I have waste time to get in touch with you. Okay.
Thank you, sir. Very kind of you, sir. Thank you.
Thank you. See you again. Okay. Bye bye. Thank you.
Thank you, sir.
Thank you.
Now we are going to start the next session. That is the last session of the Atal FTP. Now it is the time to introduce our chief guest. Good evening, all. It gives me immense pleasure to welcome you all to this faculty development program. At the outset, I extend a warm and heartfelt welcome to our distinguished resource person, Dr. Sarat Das, Professor of Statistics at the School of Mathematical and Computer Sciences, Heriot-Watt University, Malaysia. Dr. Sarat Das is an eminent statistician whose academic journey began at the prestigious Indian Statistical Institute, followed by advanced research at Purdue University, USA. Over the years, he has served at leading institutions such as the University of Michigan at the Michigan State University before moving to Malaysia, where he continues to contribute profoundly to teaching and research. His pioneering work in Bayesian statistics, temporal and spatial temporal data analysis, data science, and machine learning has resulted in numerous impactful publications. His research spans a wide range of application areas, including biometrics, health, business, and insurance. Notably, in the field of biometric recognition, Dr. Sarat Das developed innovative computational and Bayesian methods that earned him several prestigious international awards, such as the Frank Wilcoxon Prize, the Mitchell Prize, and the American Statistical Association Outstanding Statistical Application Award. We are especially honored to have with us someone who played a crucial role during the COVID-19 pandemic in Malaysia. His expertise in statistical modeling was instrumental in analyzing disease trajectories and guiding government decisions during the second wave. His contribution helped build expert analytical groups within the Ministry of Health, for which he received recognition and several awards. Today, we are privileged to learn from a scholar whose work exemplifies the power of statistics in solving real-world problems. I also extend a warm welcome to our respected principal sir, and R&D, HOD, faculty members, participants, and everyone who has contributed to organizing this FDP. Once again, I welcome you all and session over to you, sir. Thank you.
Thank you very much, Professor Dr. Mukesh. And thank you very much for inviting me over for this workshop. So thanks to you and also the organizing committee for the invitation and also for the very nice introduction. So I can begin my lecture if you are okay. I can share my slides now if that's okay. Can you hear me, Dr. Mukesh?
Yes, sir. Yes, sir. You can share your screen, sir.
Okay. I hope you can see my slides.
Yes, sir. It is visible.
Okay. All right. So let me start. A very good afternoon to everyone, afternoon and evening. So the topic that I have here is statistical time series models for many applications, including TEC prediction. So in this set of slides, I am going to talk about a basic time series models, their characteristics. I'm also going to talk about statistical models that are used to model these kind of patterns that we see for time series. And then also the estimation of the parameters involved, and also how to select a good model for the observed time series that you see. And finally, we will look at how to use this for TEC prediction. Okay. So let me begin. Time series data and their characteristics are as follows. So time series data, they consist of observations which are collected sequentially over time. So this is not cross-sectional data where observations are taken over a fixed time point. Okay, so this is a sequential process. So a salient feature of time series data is actually the presence of correlation between neighboring observations. Okay, and that is the primary objective of the statistical models, to actually capture that correlation and also use that correlation for prediction. So time series analysis, because it is ubiquitous in many, many areas such as finance, epidemiology, physical sciences, and econometrics, etc. So this is an important part of statistical analysis. And so we can actually understand the issues as well as the questions involved by looking at some real observations taken from different subject matter fields. Okay, so let me take a look at some examples of time series data that we see that have been observed in real practice. So this example number one is for Johnson & Johnson quarterly earnings data. This is a US company, and it consists of 84 quarters for 21 years. And it's measured from Q1, the first quarter of 1960, to Q4 of 1980. And if you take a look at the time series plot that I show you on the screen, you can see that the pattern that you see here are basically oscillations, which we call cycles. And these are very regular. Okay, for every year, you will see a upward trend, upwards peak, and then it goes down. And then the next year again is the same thing. So these are called cyclical characteristics, as well as if you look at the overall movement from 1960 to 1980, you can see a non-linear trend. Okay, so you can see the trend. So two characteristics is trend and also the availability of, or the presence of, cycles. The next example is global warming. These are observations in which are global mean land ocean temperature deviations. And the deviations are calculated from the baseline average year from 1951 to 1980. These observations are available from 1880 onwards to 2015. And you can see again the salient pattern here is the upward trend in recent years, especially in the later part of the 20th century. So the question here, which scientists want to answer, is that if the overall trend is natural or is it caused by human activities. Example 3 is speech data. So this is a very high frequency data. Okay, so the first two examples were slow moving trend and cycles. Okay, slow moving. All right, but take a look at this third example, which is speech data. So it gives you a 1,000 point sample in 0.1 seconds. So that's very fast. Okay, which is the sound made by human. Okay, and then they are recording the frequencies. Okay, the frequencies of that sound. And what you see is that there are very high frequencies or very high peaks. Okay, and these are also periodic in nature. All right, so the peaks are very regular. All right, followed by some lower relative peaks here. Okay, so basically this the regular repetition is known as the pitch period. So the separation between this is called the pitch period, and it's a result of opening and closing of the glottis. Okay. So the salient feature here, unlike example 1 and 2, is again the regular periodic behavior, but it's sort of very quickly varying. Okay. For later, I will refer to this picture again, and we will see some analysis based on this picture. Example number 4 is Dow Jones Industrial Average. This is financial data. Everybody is very familiar with financial data. So this is daily returns from 2006 to 2016. Okay, and you can see that the returns are basically very stable around 0. Okay, however, they incur much fluctuations. Okay, so these fluctuations are called periods of high volatility. So in statistical language, it translates to high variance. Okay, so it oscillates very quickly. It oscillates very highly over here, and you can see these clusters of volatility happening over here as well as here, and also a little bit here. So a problem in financial time series data is to forecast the volatility of future returns. Okay, next one is time series data, which involves two variables. So the first one is called the Southern Oscillation Index, or SOI. Okay, and the other one is called recruitment, which is the number of new fish in the ocean. Okay, and this is collected for 453 months from 1950 to 1987. And so the SOI measurements are air pressure changes on the sea surface, whereas the recruitment counts the number of new fish in the ocean. So you can see again here that there are cycles, and you can see there's two cycles. Okay, so one is the yearly cycle, up down, okay, up down, and the other one is a more general cycle where it goes up, then comes down, okay, and then goes up a little bit, comes down. And so this larger cycle is not yearly. The larger cycle is around 4 years. Okay? And more importantly, the reason I'm showing you the two pictures is that they are correlated. So you can imagine that depending on the air pressure, that you see in the sea surface, it is going to affect the number of new fish that is going to be in the ocean. So the two series are related, and the fish population is dependent on the ocean temperature. So for later, we will look at how to analyze this data. Okay, so time series statistical models, let's go to the mathematics of it. So we aim to develop probabilistic or stochastic models, which is able to represent observed trajectories seen earlier. So we define a time series collection like this. It extends to -infinity and all the way to +infinity. And the indices are all indices in the set of all integers. So from -infinity to +infinity at the, it's -2, -1, 0, and so forth. So we usually write it like this, yt, and then t belongs to z, and z represents the set of all integers. So I will denote this collection by this compact notation here, t goes from -infinity to +infinity, okay, to denote this series. So it just represents a sequence of observations which are going to infinity on both sides. And if there are finite series, then it starts from t1, t0 and t1, then I will denote it like this. So this is very important, the notation that I'm going to use. Okay, and in the subsequent slides, I'll give you examples of stochastic models of time series data. And the fundamental idea here is to model the correlations between the adjacent and the nearby observations, all right? The first thing that we're going to do is to model the correlations. Okay, so the first class of models is, you all are also very familiar with this. This is called the white noise model, and this models uncorrelated observations, okay? So white noise is a collection of random variables, epsilon t, t going from -infinity to +infinity with mean 0 and finite variance. So we denote white noise like this, okay? And the term derives from white light. Basically, all possible frequencies of white light, all component frequencies are present with equal strength. So another definition or term that I'm going to use is called IID, which stands for independent and identically distributed. So it means that these epsilon t's, because there are so many of them, there are this many, infinitely many of them, but we assume that all of them are independent of each other, and also they are identically distributed, meaning that all of them have mean 0 and finite variance, okay? So epsilon t, epsilon 100, epsilon 200, all have the same mean and also the same variance. So Gaussian white noise is when the distribution of the white noise is Gaussian or normal with mean 0 and variance sigma epsilon. A white noise trajectory looks like this. So you can see that the center is 0 because the mean is 0, and they show no correlation whatsoever between adjacent observations. Okay, next model is moving average, so MA. So we can take white noise process and we can apply a filter, okay, to smooth out certain values. So suppose we look at epsilon t and its neighboring values, t-1 and t+1, and we create a smoother which is called ST, which is the average of these three observations. And we plot it for t goes from -infinity to +infinity, okay? So because of this smoothing operation, what happens is that the resulting series appears smoother, and therefore we have induced correlation between neighboring observations of ST and ST+1 or ST-1, okay? So it looks less erratic here, okay, and more smooth. Okay, and now we can also do more, all right? We can create an autoregressive process. This is called an AR process, where we derive the AR process using white noise. Okay, so how do we derive this? So we say that, okay, let's define this process YT, which is its previous value YT-1, and then minus the next previous value, which is YT-2, but we multiply minus 0.9 there, okay, as the coefficient, and we add to it white noise. Okay? So the current value depends on two past values, and therefore this is known as autoregression. Okay, so when dealing with first two values, basically if you start it from yt0, then basically the first two values need to be initialized arbitrarily before you can start the process for t equals to 3 because it depends on the past two observations. Okay, so the figure below looks like a trajectory of an AR model, this one. And you can see that we have induced correlations in a certain way. And this looks like very much like the speech data that we have seen before. Okay, now, so we have looked at all this. Now we look at random walk. So what is a random walk? Random walk is a model that is given by this equation in statistics or mathematics. Yt is equal to delta plus yt minus 1 plus epsilon t. So compared to the previous slide, you can see that the difference is I've added an intercept term here, and also the coefficient of yt minus 1 is 1. Okay, right. So remember, because it depends on the previous value, we need an initial condition to start it off, which is we can take y equals to 0. And the epsilon t are basically white noise. Okay, so this model can be used to analyze the trends that we saw in the previous slides. Okay, delta, the intercept, represents a drift. This is called the drift parameter. If the drift is equal to 0, then it's just called a simple random walk. Otherwise, if the drift is non-zero, we call it a random walk with a drift. Okay, so we can write down the equation recursively. So yt recursively, you can recurse it all the way up to the initial value, which is y0. And if you recurse this over and over again, you get a linear trend, okay, delta t, and a sum of the Gaussian white noise terms, which is from 1 to t epsilon k. Okay, so I show you the trajectories in the next slide. Okay, so if you take the drift to be 0, and it is represented by the blue line. So you can see the blue line, it is centered around 0, okay? But the variability is quite large, all right? It goes all the way on both sides of the mean line, which is 0. And if you take 0.3, then it's represented by the black lines. And therefore you see a trend, all right? The trend is around delta t, okay? This is the trend line. And again, the fluctuation around the trend line is as bad as you see for the blue lines. Okay? So what this represents is that the variability of the random walk variable, which is yt, around the trend is sigma squared t. So as t increases, the variability actually increases quite a bit. Okay. All right, next we want to model. So this one was a model for the trend. Okay, I haven't showed you how to model it or estimate it, but let us try to understand some fundamental processes first. Okay, the next one we want to do is for the cycles. So this is called periodic signal with a noise. And to model periodic cycles, you can take a look at this model, for example, yt equals to 3 into sine of 2 pi, t plus 15 over 24 plus white noise. Okay, so if you have a sinusoidal waveform, then it is basically periodic in nature, where A is the amplitude, and then W is omega is the frequency, and phi is the phase shift, which is the start of the curve. The curve may not start at 0. Okay, so the curve may start at some other value, non-zero, and that is represented by the phase shift. So in the above model, A is 3. The frequency is, of course, 2 pi divided by 24. So this is basically 24 means 24 hours in a day. So this is representing some kind of daily cycle. Okay, so that is one cycle is completed every 24 months. And then the phase shift or the phase difference is 1.2 pi. That means y0 is actually starting not from 0, but an initial value, which is 3 into sine 2 pi, 1.2 pi. So this is negative. So you can see that this is the deterministic sinusoidal curve. you can see that the phase makes it start at a non-zero value here, and then the oscillations go like this, right? And the period is going to be basically 2 pi over 24. Okay, and then if you add noise to it, which is normal 0, 1, then you get cycles, right? But a noisy version of the cycle. And if you add more noise, then basically it becomes more distorted and the cycles are not so clearly seen. Okay. All right, so we are going to look at statistics. We are going to look at a probabilistic framework or statistical framework in order to analyze this kind of models as well as observed data. So here is a general definition. A stochastic process YT and T belongs to a set I is a collection of random variables indexed by T, and it takes values in the index set I. Okay, this is a very general definition. So, and YT, okay, takes values in a range set, which is called B. So for the stochastic processes that we looked at, which were discrete time series, basically the index set was Z, okay, and the set of the range set B was basically the real line, because all of the data, the YT, took values in the real line. Okay. Now, in probability, we want to characterize the stochastic process. And the characterization of a stochastic process is complete, or it is completely characterized by its finite dimensional distributions. Okay, so what are finite dimensional distributions? These are quantities like this, which is for any index T1, T2 up to Tn coming from the index set of Z, and for any value of Y1 up to Yn coming from the range set of Y, okay? If you specify the probability of all such values, okay, for every value of T1 up to Tn, and for every value of Y1 up to Yn, if you specify all of this, all right, then the stochastic process is completely determined. Okay, so the distribution is well known. Okay, so the joint distribution functions describe the observed data completely, but of course, I mean, there are so many parameters here to specify, so they are difficult to analyze. So we need some simplifying assumptions about the processes, and we use only univariate and bivariate measures. Okay, so just like I mean, mean, standard deviation, and correlations are very easy to understand. So in the same way for time series also, we summarize everything in terms of means, standard deviations, and correlation. Okay, so first of all, the distribution functions of univariate marginals, which means just a particular value of just one particular T, okay, and one particular Y, all right? And that is this. So this is called the univariate marginal distribution. And we want joint because we are going to look at correlations. So this is the joint distribution respectively. All right, so so now we know about averages. So let's look at the mean of YT. The mean of YT is denoted by mu of YT, and it is basically the average with respect to the distribution of FT, okay, at time point T. So that is given by this. And the variance of YT is given by our usual formula of the variances. But now this is when the distribution is discrete, and this is when it is continuous with a PDF. Okay. So we have defined mean and variance for every value of T in the range in the index set, which is Z. Okay. All right. So we have defined that. And now we look at covariance, which is autocovariance, because the term auto means that you are looking at the same time series, Y, and you're looking at covariance at the different time points. So the covariance between YS and YT, we denote it like that, sigma of YS YT. And this is just the formula for covariances, okay, but applied to time series models. So using the above notation, if you now write ys to be equal to yt, then you get in this expression the variance. So sigma of yt is actually the variance, right? And now the correlation between ys and yt, the autocorrelation is basically this entity here. All right, it's the autocovariance divided by the square root of the variance of ys and the variance of yt. Okay. Okay, so for one process, you have yt, which we can compute the covariances and the correlations of yt with itself. So that's called auto, okay, auto covariances and correlation. But if we have two processes like we saw in the case of soy and recruitment, all right, the fish, number of new fish in the ocean, then we can look at cross covariance. Okay, so the cross covariance between two time points and also two variables, xs and yt, is given by this formula. So it's denoted by this, and it is the covariance between xs minus xs and yt. Okay, and we define it as sigma xs comma yt. The correlation between them is the covariance divided by the square root of the variances, the corresponding variances. Okay, so the random variable subscript that you see that I've defined so far is the notation of mu for the mean and sigma for the variances and covariances. So we will use this notation throughout. Okay, so when there's no confusion about which process that we are talking about, whether it's the x or the y, the notations I'm going to drop. So mu of yt will be just mu t, and sigma ys yt will just be sigma st when it's understood that we are dealing with the y process. So let us look at the mean and autocovariance of white noise. Okay, so because I told you white noise is independent and identically distributed, there's no correlation between them. The covariance between any two white noise variables when s is not equal to t is 0. And when s equals to t, it is the constant variance because it represents the variance. It is the variance. And let's compute the covariances of other processes. So for example, if you have u to be a linear function of x's, for example, this is just general x, and v to be a linear process of y variables, then the covariance between u and v can be written in this form, where it is the inner product between, or the product between ai bj, and then the covariance between xi yj, and then you sum over all indices I, and you sum over all indices j. And if you want to compute the variance, then you just replace this v here by u, and using the same formula, you get this expression here. The bj becomes aj, and then you have covariance of xi xj, right? So let's recall the mean and covariances. We want to calculate this for the moving average. So recall that ST is equal to the average of the first of three neighboring white noise variables. So the mean of ST is going to be 0 because you're looking at the expected value of this, the sum of the expected value of the sum is the sum of the expected value. All of them are 0. So this is 0. And the autocovariance is basically the covariance between the tth index, time index, and the asset time index. So if you take a look at this, all right, and now the covariance is a bit complicated, but not too bad, because we are going to look at overlaps. So when S and T, the indices are greater than 2, there is no overlap, right? Because all of these three indices do not overlap with these three indices, okay? So they are all independent of each other. That means the covariance is equal to 0. Now, if S is equal to T, then you have the same terms here, all right? It is 1/9, because you can take 1/9 out, 1/3 from this expression and 1/3 from this expression. Right now, we want to calculate the covariance between the linear terms here. So the formula that I explained, showed you over here, you can use, okay? So basically, it's the covariance between this and this, okay? And then this and this, which is 0, this and this, which is 0, this and this, 0, this and this, which is this term here, and then this and this 0, this and this 0, this and this 0, and this is the term that is non-zero. So you can see there are 3 terms that are non-zero. So it will be 3 into sigma epsilon square divided by 9. When S is equal to t plus minus 1 is the adjacent one. So we can calculate the covariance at time point t minus 1 and time point t. So this is time point t minus 1. So you have epsilon t minus 2, epsilon t minus 1, and epsilon t. And this is epsilon t minus 1, t, and t plus 1. Okay, so again, apply the same formula for the covariance. This and this is 0, this and this is 0, this and this is 0, then this one and this is this term here which survives. That's non-zero. And you can see the final term that survives is this epsilon t term. So that survives here, and the covariance is given by 2 over 9. Okay. Similarly, if you look at, okay, so now the result is also true if you take, instead of t, you replace t plus 1. So you shift this by a unit. All right, so t minus 1 becomes t, and t becomes t plus 1. The result is also true. You can verify that. So we get the result here that the covariance, whenever the S and T differs by 1, you get that the covariance is equal to 2 over 9. Whenever the S and T differs by 2, okay, we can similarly show that the covariance is 1 over 9. So we sort of consolidate all the results that we get here. So we can see that the covariance terms is 3 over 9 if S is equal to 3 over 9 sigma square if S is equal to T, 2 over 9 sigma square if S and T differs by 1, and sigma square over 9 if S and T differs by 2, and in all other case it is 0. Okay. All right, so this is the covariance structure of a moving average process. So now if we take the absolute value of S minus T, you can even simplify further. You can see that the covariance between S and T does not depend on S and T. It actually depends on the difference between them, the absolute difference between them. So you can write down the covariance terms as a function of the absolute difference between them, which is H. Okay, we write it. And you can write down the 3 terms, and you can say that when H is 0, it is 3 over 9 sigma square. H is 1, it is 2 over 9, and this one. So this is very important because this is the crux of the matter for covariances. You will see later when we have stationary processes. Okay, so the smoothing operator gives rise to a covariance function that decreases as a function of H, which is the absolute value of S minus T or T minus S. It doesn't matter which one it is. And the covariance becomes 0 when H is greater than or equal to 3. Okay. So note that the autocovariance depends only on the time separation lag, and it doesn't depend on the actual values of S and T. Okay. And this functional form suggests a mathematical model for weak stationarity. All right. Next example is the mean and covariance for random walks. Okay, let's try to find this out. Okay, so the random walk model, if you remember, was given by a trend component, which is delta into T. This was the trend component. And then a stochastic component, which is cumulative, which resulted in the variance also becoming large as T increased. Okay, so since the mean of the random walk is 0, mean of the Gaussian white noise is 0, and delta is a constant, so the mean of the random walk process is around the linear trend. Okay. That's what we saw in the picture. Okay. Let's take a look at the covariance. So we want to calculate the covariance between S and T. Okay, so that's between YS and YT. So for covariance, the mean doesn't come into play because the mean is subtracted from the random variable. So it's always the covariance between the stochastic part, which is the sum of the Gaussian. the sum of the random white noise variables up to S and the white noise variables up to T. Okay, so if you calculate this covariance, you will see that it is actually the minimum of these two indices, S and T, into sigma square. Okay, so I mean, it's very easy to take examples. So if you take S is equal to, let's say, 3 and T is equal to 5, this is the sum of 3 Gaussian white noise, and this is the sum of the same 3 plus epsilon 4 and epsilon 5. But epsilon 4, 5 is uncorrelated with the first 3. So the covariance basically is the variance of the first 3, which is 3 into sigma square. Okay, so what is 3? So this was 3 and this was 5. So minimum of 3 and 5 is 3. So that is how to calculate this formula here. And what to note is that the autocovariance function in this example for the random walk process does not depend on the difference of the two time points. Okay, and this is going to show that this is not a stationary process. Although I have not defined stationarity, but I'm going to show you the definition. I'm going to give you the definition soon. Okay, all right. So this is not stationary. Okay, and the variance is, of course, linear in T. So basically, it is increasing in terms of T. All right. So because variances are actually unbounded, it can become very small or large. We like to talk about autocorrelation. And this is a fundamental quantity called the autocorrelation function, the ACF. Okay. So it is a measure between -1 and +1, just like regular correlation. And it is defined by the autocovariance between time points S and T and divided by the square root of the variances. Okay. So again, as in cross-sectional data, if YT and YS are completely dependent on each other in this way, then the autocorrelation is going to be 1 if this coefficient is positive, and if it's going to be -1 if this coefficient is negative. Okay, so this autocorrelation function gives you a measure of forecastability of future values based on the past values. Okay, so if we have two processes, the cross correlation function is called CCF. Is the same notation here. Is the cross divided by the square root of the variance. Again, if YT is linearly related to XS, then basically the cross correlation function will be 1. Otherwise, it's going to be -1 depending on the slope of the explanatory variables. Okay, so I've talked about all of this, and now I want to go back to distributions. Remember, we have simplified the distributions in terms of means and variances. However, they are still not enough because the means are also functions of T, okay, and the covariances are also functions of T and S. Although it is a function of H for stationarity, it gives you an idea about what we need to do next, right? So basically, I want to give now the definition of stationarity. There are two definitions of stationarity. First is strict stationarity, where again, if you look at the collection of random variables, which is YT1 up to YTN, and I told you that the entire stochastic process is governed by the distribution of all of these random variables for every collection of T1 indices, T1 up to Tn. Okay. So what we're going to assume now here is that this collection is going to be invariant. The distribution of this is going to be invariant when we shift it by H. So let's say we have Y1, Y2, Y3, and if we impose stationarity, it means that the distribution of Y1, Y2, Y3 should be the same as distribution of Y100, 101, and 102. Okay, so that is the assumption here or the restriction here, right? And therefore, what it does is that it gives you that all the marginal distributions should be same, And that means that the means are all going to be just a constant. Okay, so mu t was the mean of yt at time point t, so it is going to be just a constant. Okay, and then also we imposed it for oh dear, I don't know what I did. Okay, anyway, right. We imposed for any variables here, any number, we only need it for 2. So if you look at joint distributions, let's say y1, y2, then the distribution of y1, y2 should be the same as distribution of y100, y101. Okay, or y1, y3 should be the same as y5 and y7. Okay, so those kind of restrictions when we are basically putting a restrictions on the covariances. And this restriction tells you that the covariance is basically a function of the difference, absolute value of the difference, which is h, which is s minus absolute value of t minus s. Okay, so weak stationarity is a relaxation of strong stationarity. Basically, it says that instead of putting an assumption on all the distributions, we put conditions on the first 2 moments only, because that's what we are interested in. Okay, we say that the mean is constant, it doesn't depend on time t, and also the covariance depends only on the difference of the absolute value of t minus s or ts. So if a process satisfies these 2 conditions, then we say that the process is weakly stationary. Okay, so weakly stationary is the starting point of our statistical analysis. So we will, when we say stationary, in this case, we will actually mean weakly stationary. Okay? And if something is strict stationary, I will use the term strict stationary. Right? So if we go back and we see over here, the moving average, you see that the mean, okay, the mean of moving average was 0. So it is a constant in as a function of t. And you look at the autocovariance function, you see that it is a function of the difference between s and t. So that is, so it only depends on h. So you can see that the moving average process, which is st here, all right, is stationary. Okay, so this process is stationary. If we look at the random walk, we see that the covariance function cannot be written as the difference of the absolute value of s minus t. So this process is not stationary. And also you can see that the variance, remember, if you look at stationarity, then all of the distributions for every value of t is common, right? But immediately you see that here, it depends on t. The variance depends on t. So that means the distribution of yt is changing as a function of t. So it cannot be stationary. Okay. So stationarity is actually a very stable process. If I plot a stationary process, it will just be stable around the mean value, right? And what we have for a stationary value, we use statistical methods to estimate the correlations between neighboring observations. The autocorrelation function of a stationary process is like this, okay? So remember that it depends on the covariance divided by the square root of the variances. So, and this term depends only on h, and these terms don't depend on t, so it is equivalent to putting a 0 here, right? So it's a simple form of the autocorrelation function. Okay. So for white noise process, it is the indicator function. So basically the covariance is sigma square if h equals to 0 and 0 if h not equals to 0. So this is if you plot the autocovariance function, you'll get a spike at 0, and then the remaining part is all just, okay, 0 values. And here, so if you plot the ACF also, you'll get 1 at 0. So it's an indicator function at 0, okay? And then at other values, it just takes the value 0. So it's a point mass or a delta function at 0. For the other processes, they are not so non-smooth. So this one is 0 or 1. Okay. For the other processes, okay, for the moving average process, as I mentioned to you, right, the autocorrelation function is going to be 1, 2/3, 1/3, depending on the value of h, right? And because we are looking at stationary points from -infinity to +infinity, right? So you can look at this autocorrelation function is symmetric around 0. Okay, so let's discuss a little bit about the non-stationarity of random walk and something we call trend stationarity. So as I mentioned, the autocovariance function of a random walk is this. So it can't be written in terms of, so h is called the lag, right? So it cannot be written in terms of the lag. Okay, and also the mean function is not constant as a function of time, and neither is the variance. However, some series may exhibit non-stationarity only through the trend. So here's an example. Suppose we have WT, which is a linear trend, plus YT, which is stationary. Okay? So then the mean of WT is like this, and it's non-stationary because it actually depends on T. Okay? Right? So it's a linear trend, it depends on T. So it's not, WT is not stationary. However, if you look at the autocovariance function, okay, autocovariances does not depend on the mean because the mean is subtracted out. Okay. Right. In that case, you can see that the autocovariance function of W is the same as the autocovariance function of Y, which is a stationary. So it depends only on H. So there's a stationary behavior around the linear trend. Okay. Let's take a look at joint stationarity. So two series are said to be jointly stationary if each series is stationary, and also the cross covariance function is a function of H, right? So similarly as before, you get a cross covariance function in this way, right? And what is true is if you have gamma of X and Y at a lag H, then it is the same as when you invert this to Yx and at minus H, okay? And since this is the rule for covariances, if you apply this, you will get this identity. However, if you don't switch the indices or the notations X and Y, then in general, the cross covariance of X and Y at H is not the same as the cross covariance at minus H. And you will see an example later on in terms of what predicts what. Okay, so correlation, the same thing, right? You have cross correlation is between 0 and 1, and this is the case. Okay. So let me give you an example of joint stationarity. So you have two time series as like this. So you have XT, which is a sum of two white noise variables, and YT is the difference of the same two white noise variables. So what we are going to have is the variance of XT is the same as the variance of YT is equal to 2 times sigma square. And the autocovariance function of X is going to be sigma square, okay, at value 1. And the covariance of Y is just the reverse of X, right? Because there's a minus here. So that's going to be minus of sigma square. Okay, it's very easy to see because if you look at XT and XT plus 1, then you can see that XT plus 1 is epsilon T plus 1 plus epsilon T, and XT is epsilon T and epsilon T minus 1. So the only term that is common to both XT and XT plus 1 is epsilon T, and both are positive. They have positive coefficients, so that's why these values are all positive. The correlation between X and its lag 1 is positive. But Y, if you look at the same way, YT plus 1, the coefficient for YT plus, the epsilon T for YT plus 1 will be negative, and that gives this result right here. Okay. So the cross covariance between X and Y you can calculate is given by this, right? And in the same way, the cross covariance between X and Y at -1 is going to be sigma square. It is not minus sigma square. So that emphasizes what I said in the previous slide, that the cross covariance between X and Y at H may not be the same as the cross covariance between X and Y at -H. Okay, so the correlation function looks like this. Okay, again, it depends only on H. So this time the two processes are jointly stationary. Okay, so I want to do some prediction here. Suppose that YT is depending on A and then multiplied by XT minus L into epsilon T. Okay, so looks like XT is predicting YT. Okay, so if this L is positive, then we say that XT leads Y. Otherwise, it's said to lag. That means YT is going to predict XT. Right, and the cross covariance function between X and Y, you can calculate and get it to be A times the autocovariance of X. So the cross covariance looks exactly like the autocovariance. Okay, so if L is positive, then X will lead Y. Otherwise, Y will lead X. So here is a good example. Suppose I have a series X, and this is my autocovariance function of X, and you can see that over here, this is the autocovariance function. Okay, there's a peak at 0, and then it goes down, and it's all very close to 0. But then the cross covariance is basically this multiplied by H minus 5. Right, so this pattern over here, the peak, will be represented here. Okay, starting from 5. All right, so if you see something like this, then we always know that in this example, X is leading Y, so X is good for predicting Y. So if this is positive, then X here is going to predict Y. If it goes negative here, the peak is negative, then Y is going to predict X. Later on, when you look at these plots, the plots are always called Y and X, never X and Y. Okay, so please remember that this is not X and this is not Y here. Otherwise, you will mislead what is leading what and what is lagging what. Okay? So in this example, if you see plus here, this is X, whatever variable is here is going to lead this variable here, which is Y. If it's here, all right, this variable here, Y, is going to lead this variable here, which is X. I hope that was clear, right? So we look at estimation now. So how do we estimate this based on data? Please remember that we have only one trajectory, which is quite long, okay? So we have N very large. But based on this trajectory, we have to estimate all of these autocorrelations and mean and everything. So the assumption of stationarity becomes very crucial, okay? And these are the estimates. The sample mean is estimated by the population mean is estimated by the sample mean, okay? And the variance of the sample mean is this expression right here, okay? And the autocovariance function is estimated by the sample autocovariance function, which is given by this formula here, okay? All right, so because it's lag H, you can only go, if you look at YT and YT plus H, you can only look at N minus H of them, okay? And then you just pretend that these are two separate samples and you calculate the covariance between them. This is the formula for the sample covariance, right? And the sum is only up to N minus H for different values of H, the lag. And the crucial part here is we don't divide by N minus H in time series. Okay, this is a fundamental difference in time series compared to cross-sectional data, because there's a property of this autocovariance functions which is called non-negative definite. And the population covariances are non-negative definite by default. But then we also want the estimates to be non-negative definite. So if you divide by N minus H, they lose the non-negative definiteness. Okay, so we need it to be non-negative definite for reasons you will see later. All right, so we divide by N. Okay. So the sample autocorrelation function is given by this. Okay, and what is very important for the sample autocorrelation function is this rule here: when N is large, and suppose that the original process has no correlations at all, okay, then the sample autocorrelation function actually has a normal distribution with mean zero and very small variance. Okay? So what you will see later in the ACF plots is that there will be a boundary line which is plus minus 1.96 into square root of n, which is coming from this result. And that indicates the limit of it being zero, right, when it is white noise. So if you see something that crosses that peak, then you know that that lag is very significant, right? And you have to take into account that lag. The process of estimation, as I've explained to you before, if you want to estimate lag H, you take this pair from your single trajectory data, and then you just calculate the covariances as you do for sample covariance, minding that you divide by n instead of n minus h. So in this case, the correlation lag 1 is 0.6, and this is 0.84. Okay, for the ACF for the speech data is like this, and you can see that the periodicity is very well captured because the ACF is periodic. So a periodic signal will reflect in a periodic ACF autocorrelation function. Okay, so there's a repeating peak. You see here, this is a main peak, and then the same peak is being repeated at an interval of 106 to 109 points. And this is the frequency which corresponds to the pitch period. Okay, so the pitch period is around 100 points. So each one is 0.1 seconds. So it's about 0.01 seconds. There are 1,000 points per second. So this is the pitch period. So it's very fast. Cross covariance function, the same analogy is, okay, so we divide by, we don't divide by n minus h, we divide by n, and we still have the same result for the estimates of the cross correlation function. If it's spurious, meaning that if the underlying process is white noise, one of them is white noise, then the cross covariance function will not pass the limit here, okay, which is the same limit as before. Okay, so I'm going to show you some examples. Remember, we went here. So I'm looking at the soy oscillation indices, and also I'm looking at the recruitment. And I want to look at the cross covariance functions as well as the cross correlation function here. Right, so let me go back here. And we see that the ACF, as expected, is periodic. This is the southern oscillation function. So you see it's periodic. And this is what I was explaining, that the original series has annual fluctuation. So you see that at time points one here, the period of this trajectory is actually 1. Okay, so it repeats itself after every 1 unit of time, which is the annual cycle. For recruitment, also you can see some little bit of oscillation. So you can see some oscillations here, right? And also this is periodic in nature, but after this point it disappears. But there is still periodicity here, which is the cycles. Okay, and if you look at soy versus recruitment, remember soy is Y and recruitment is X, okay? And you can see that the highest peak is a negative lag here, okay, for the cross correlation function. And it also exhibits periods. So you can see that the period is somewhere here about, this is -1 somewhere here. So this is about minus 0.5, about 6 months, okay? So what is leading and what is lagging? So lag is negative. So that means Y is leading X. So soy, the oscillation air pressure is actually determining the recruitment of fish or the number of new fish. So it becomes clear what is leading what and what is lagging what by plotting all these functions. And this blue bands is the confidence band. So anything above the blue band is significant. You have to model that. Okay, so you can see that here, this soy leading with this lag is actually the most important thing that you should capture. Okay. All right. So I think I've explained all of this. Okay. And you can take a look. Right. So let me formally describe autoregressive models. So we give a general class of stationary process. It's called the autoregressive process. As I mentioned to you, this is called autoregression. The process YT depends on previous values and also and added with a white noise process. Now you can more generally define a order P autoregressive process depending on the past P value. So here is the definition of autoregression. Okay, YT is a function of YT minus 1, YT minus 2 up to YT minus P plus epsilon T, and epsilon T is white noise. Okay, so the above process, it has mean 0. If you want non-zero mean, you replace each of this YT by YT minus mu, its common mean. So the process becomes like this, or equivalently, we write it in this way where alpha is related to the mean in using this formula here. I also want to talk about how to represent this process in mathematically. So I talk about the backshift operator. So the backshift is basically taking YT and applying B, and you get YT minus 1. So if you apply powers of B, you get previous values, right? And so on. Okay, so B inverse is the forward shift, B is the backward shift. So we can write this in terms of the backshift operator. Put everything on one side and put epsilon T on this side. And the entire thing here can be written as a polynomial related to the backshift operator. So an autoregressive process can be notationally, you can concisely write it in this way. Okay? So this is the representation of an autoregressive process of order P, where this is the polynomial of order P in terms of the backshift operator. Right? So if you example is AR1 model, so you have YT equals to phi of YT minus 1. Okay, so you can recurse. And if you recurse to infinity, you are going to get this linear representation for YT in terms of the white noise process. So it is J equals to 0 to infinity, phi to the power of J, epsilon T minus J. Okay, so this is the stationary solution of this process. Okay. So the mean is 0. It's okay. And the autocovariance function is the covariance between YT and YT plus H. So because you wrote it in this form, this is a fundamental form. It's called a linear process form. All right. It's very easy to determine what the covariance function is because it's the covariance between some linear terms. And I've already given you the formula for covariance between two linear terms, two random variables, which are composition of linear terms of some other underlying variables. So you can do this expression and you can do this simplification and you can get this as the covariance. Okay, so it's sigma square phi to the power of H divided by 1 minus phi square, and it only depends on H, which is the lag. Okay. So the ACF is looking like this, right? And it is a function of only the lag, which is the absolute value of S minus T. So the mean is constant. The ACF is a function of H only. So this is a stationary process. So ARP is stationary, provided that this phi is less than 1. Okay, I will explain that a bit later. Right, but these are two sample realizations of AR1. If you take phi to be 0.9, then it's positive correlations between YT and its neighbor, so you get something smooth. But if you take phi to be minus 0.9, then it is very, the neighboring ones are negatively correlated, so you get very, very rigid oscillations, okay, between one another. Okay, now I want to talk about non-causal versus causal AR process. Okay, so if we take a look at a AR process where phi is, let's say, 2, okay? Okay, so are these stationary or non-stationary? Okay, so you can recurse as before, all right? But you're going to get the same kind of linear process. But now because phi is, let's say, 2, 2 to the power of j is actually diverging. Okay, it becomes infinity. So this process does not converge. Okay, all right. However, you can write down this process, the YT process, like this. Okay, because you take 2, if you do 1/2, then it becomes convergent in some sense. So the past value can be written in terms of a future value and the white noise process. And this coefficient, because phi is greater than 1/phi will be less than 1. Okay, and then we can recurse, and the recursion is going to be like this. But now the problem is YT depends on future values. It doesn't depend on past values. This is a stationary process because now phi being 2, all right, is raised to the power of minus j. All right, so 1/2 to the power of j, it goes to 0. So this is a convergent process. However, this one, it depends on future epsilon. Okay, and this is actually useless for us for prediction. Okay, because you can't predict based on future values. We can only predict based on past values. So this example is a non-causal. It's stationary, but it's non-causal. Okay, so it's useless for the purpose of forecasting. So for forecasting, we need an AR process, okay, which is stationary, and also we need it to be causal. So the necessary conditions for a causal AR process is the following. I'll just give you an example. So look what we had. We had the polynomial phi in terms of the backshift operator. All we need to do is we need to take this and put it on this side and with an inverse. So we need the inverse to exist. That's all that is. Okay. So if the inverse exists, then this YT process will be causal. Okay. And in the example, the AR1 process, if you look at the inverse, it is 1 minus phi times the backshift operator raised to the power of -1. And that is given by an infinite series expansion. Okay. But this infinite series converges only if phi is less than 1. Okay. Okay. So this is the original backshift, polynomial. This is the inverse. And this term, this is going to be a proper inverse if this thing converges to 1 or this thing converges to 0. And this thing converges to 0 only if phi is equal to 1. Okay. So a necessary condition for AR process to be stationary and causal is that this phi should be less than 1. Okay. The absolute value of phi should be less than 1. Okay, let's move on to the moving average process. For moving average process, we have MEQ. Okay, so these are the moving average processes. All right, so we have white noise, and then we have θ1 up to θq to be the parameters. So using the moving average operator, we can write it in this way. So unlike ARP, MA is stationary for all values, and the covariance and the autocorrelation function is given in this way. Okay, so these are the trajectories, and this is the autocovariance function for a MA process. Okay, for MA process, we have a different problem. The problem is they are not uniquely identified. All right, so because if you look here, this MA process has this autocovariance function, but if you put, let's say, θ equals to 5 and sigma square equals to 1, it is the same autocovariance function when you put θ equals to 1/5 and sigma square equals to 25. So this gives non-uniqueness in distribution for the MA process, and which one should we prefer? And we come to this concept called the invertibility of a MA process. All right, it's the same thing as before. YT should be, so remember in a MA process, YT is θ b into epsilon c. You should be able to take this, put it on this side and be invertible. Okay, so again, same idea, all right? For this infinite series to be proper existing, you need the absolute value of θ to be less than 1. So we will choose the second MA process as the one that we want, so because it's invertible. Okay. So there is a relationship between these polynomials in terms of the backshift operator and also the polynomials in the complex plane, which is in terms of a complex number, which is Z. So when we want the series to be convergent, basically we want this to be true for the unit disk. And a necessary and sufficient condition is that the zero of, remember we have to take the inverse here. So the zeros of this polynomial should be outside of the circle. Similarly, if you want the inverse of this one, right? So the zeros of this should also be outside of the circle, right? So we look at a moving autoregressive moving average process of order P and Q. So remember, it is stationary. If it has this form, okay? It is stationary, definitely, right? But it is also causal and invertible if these polynomials have roots outside of the unit circle. Okay, right. So, all right. So that is the ARMA process of orders P and Q. Right. So now with ARMA process, there's a problem with redundancy. So, for example, if I look at this process here, then you might think that this is a ARMA 1-1 process, but it is not, because it is over-parameterized. So if you look at the trajectory I gave you before and I fit a ARMA, you will see that the coefficients of AR1 and MA1 are very significant. Okay? So that is not good. Okay, but you look at the coefficients here, they are very close to each other. That tells you that there's something wrong here, right? So if you now look at the fitted model, it looks like this. Okay, this is the R1 process, theta phi of P, this is that, and theta of B is like this. So you can see that this term is actually very close to this term, and they're going to cancel each other, right? And white is just actually white noise. So overall, we observe the following problems. The MA model are non-unique, but you have invertibility to actually get rid of non-uniqueness. The AR model are non-causal, but we have a restriction to make it causal, and parameter redundancy of the ARMA model. All right, for this one, we have something called AIC to reject the models that are overfitting. Okay, so this is an example of overfitting. So here is an example of overfitting. So there are examples where a simpler model will be selected based on AIC. Okay, so these are all mathematics, and I will skip this part because I think I'm sort of out of time. But these are all mathematics for the invertibility and redundant causality of terms. So you can take a look at all this since this is being recorded. Okay, and what I want to say is that you can, for a non-causal and invertible process, you can write everything in terms of a linear process like this. And in the linear process, once you get it in the linear process, you can write the autocovariance very simply in this way. Okay, and this is what we need. So for the autocovariance of a pure MA process is like this. Yeah, so it actually, if you look at the autocorrelation function here, it truncates at Q. Okay, and for the ARMA process, AR process, it actually, you need another function called the partial autocorrelation function, which will truncate at P. So let me now talk about the autocorrelation function, the partial autocorrelation function. Okay, so this one, partial means that suppose we have 3 random variables, X, Y, and Z. What we do is first we regress X on Z to obtain the predictor, and then we get the residuals. Okay? And similarly, we regress Y on Z and we obtain its residuals. So the partial correlation, because we have eliminated the effect of Z, is given by the correlation between X, the residuals of X, and the residuals of Y. Okay, so it's called the partial correlation between X and Y given Z. Okay. Right, so what we have in the case of, so the partial autocorrelation of a stationary process, okay, now it is, so let's take a look at yt and yt plus 1, okay. So there are no intermediate values. So the partial correlation is defined to be the autocorrelation, okay. But however, if you have, let's say, yt and yt plus 1, well, there's something in the middle, which is, yt and yt plus 2, there's something in the middle, which is yt plus 1. So what we do is we take yt, we regress on yt plus 1, we get its estimate. And then similarly here, we look at yt plus 2, and we regress yt plus 1, okay? So we regress all the variables which are in between yt and yt plus h, and whatever, so the residuals that we form, right, they are called partial residuals, and we look at the correlation between them, and these are called partial correlation values. So partial autocorrelation values. So why do we use double script? It will become clear later. Okay, so for PACF, I just want to show you what is happening. Very simply, the mathematics is all here, but it's easy to just show what's happening. Okay, so first of all, if you look at regression of so y2, yt plus 2, so we have yt and is a AR1 process. Okay, all right. So let's take a look at the partial autocorrelation between yt and yt plus 2. Oops. Yt and yt plus 2. Okay, so the intermediate value is yt plus 1. Okay, so when we regress yt on yt plus 1, we can write it in terms of like this. Okay, right. So this one is regressing yt plus 2 on yt plus 1. We write it like this, right? And we minimize with respect to beta. And what happens is that we get beta equals to phi. Okay, I just want to intuitively explain to you. Because you have autoregression, when you look at yt plus 2, well, the autoregression tells you that it is phi times yt plus 1 plus epsilon t plus 2. So when you regress of yt plus 2 onto yt plus 1, the regression will be this model itself. So it is no surprise that beta is exactly equal to this. Okay. All right. So when you regress, you are going to get beta to be equal to phi, and in the case of yt plus 2, and also the same for yt plus 1. So we get the correlation between the residuals like this. And the reason now the thing happens is by causality. Okay, if you take a look at this residual here, this is essentially the ARMA model, AR model. Okay? This is essentially epsilon t plus 2. Okay, and these are values which depend on epsilon t plus 1, epsilon t minus 1, and so on. And the epsilons are all independent. So the correlation between them is 0. Okay. So for a AR1 process, if you calculate the partial autocorrelation, then the first value will be non-negative, non-zero, and all other partial autocorrelations will be 0. And this actually gives you a way to determine the value of P for ARP process. So these are all the mathematics here. I'm not going to talk about this, but that's the basic idea that, so actually causality is actually very important because this epsilon should actually be independent of the remaining ones to give you a 0 for the partial autocorrelation function. Okay, so this is the behavior of the ACF and PACF. PACF is the partial autocorrelation function. So for ARP, the autocorrelation function is going to tail off. For MAQ, it cuts off, as you have seen before. For ARMA PQ, it tails off. The partial autocorrelation at ARP, it cuts off because that's what we looked at here. And for the MAQ, it tails off. And for ARMA, PQ, it also tails off. Okay. All right. So these two properties here are the ones that we are going to look to determine P and Q. All right. The next part is about prediction and forecasting. So I'm quite out of time, so I'm not going to discuss the mathematics here, but basically you can use your ARMA to actually forecast. So I've got a lot of slides on that. You can take a look and do the forecasting, okay, for all this. The point in forecasting is that basically for long range forecasting, because this is a stationary process, it will revert back to the mean, all right, and the prediction error will revert back to the original covariance matrix. Okay, so let's take a look at example of forecasting. This is the fitted data model for the recruitment data, the new fish species. Sorry, the number of new fish. So in this case, the prediction model is also the same. And the forecast mean error also satisfies a recursion. So you can see that if you apply the two equations here, I'm trying to predict. Okay, so you can see at this point, the prediction goes up, but it quickly converges to the mean value very quickly. Okay, and the confidence band will be the basic variance values of the original series at time point 0. So the bands will just be flat like this. Here are the codes that I used. I usually use R. Okay, so you can install this library and use my codes in order to get all the prediction values. You don't have to know the mathematics because everything is coded for you, right? So it gives you the prediction error as well as the standard error. I mean, you need to know the mathematics, but it will probably take more time to grasp everything. Okay, so I want to now estimate parameters. So I want to estimate the phi and the theta parameters, right? And you know that the sample mean was this, okay? And the way to do that is to use the Yule-Walker conditions, right? And I will not give you, so there's a way to estimate. These are all estimations. Okay, so these are called method of moment estimates. But method of estimate moments are not, estimates are not stable. So we have another framework which is called the maximum likelihood estimate. Okay, so the maximum likelihood estimate, let me just illustrate for AR1. Okay, in the AR model, if you want to estimate mu and phi, okay, we write down the likelihood, which is the distribution of all the y's. Okay, so the distribution of all the y's depend only on the parameters, mu, phi, and the error variance. And if it's Gaussian, we can write in terms of the Gaussian kernel, right? So there are two ways of estimating this, basically using something called unconditional sum of squares, where you need the expression of the distribution of y1, okay? Or there is a conditional, okay, so then for unconditional, this is the likelihood, and then you maximize the log likelihood, and you get the maximum likelihood estimate of mu and phi, and then the estimate of the sigma square is this. Okay. The other one is the conditional likelihood, where you condition on y1, okay, the value of y1. That's easier. So that is, okay, you can get the same estimates here, right, corresponding to mu and phi and also sigma head square. All right, so the estimate of these parameters can be done generally. So this is all this notation in the math here. But I like to give you an example. All right, so this is fitting the glacial varve series. There are 634 years, and this is the original series. So you can see that there is non-stationarity here. So in order to get rid of non-stationarity, we look at the differences, which is, first of all, we do a logarithmic transform, then we take the difference here. So it's like this. And then what turns up is a process like this is stable around 0, right? And it is fluctuating quite stably around 0. So constant mean, constant variance, right? So we are only interested in the correlation. Okay. So when you calculate the ACF and PACF, you can see that the different series, you can see that for the ACF, there is one signal here, which is significant. So that's one, leg one. And the PACF is decaying to 0. So the ACF cuts off and the PACF decays to 0 is a classic example of MA1. Okay, because of this peak at leg 1, okay, you know that MA1 is the suitable process. So you can fit MA1 process, which is like this, and the function to fit is called ARIMA. Okay, and you can fit in the data, which is Y, and then you put in the order. ARIMA, remember, it is this is P, this is D. D, I will explain to you what is D, and this is Q. So for us, we don't have any D. There's no differences. So you put 0 for P and 1 for Q because of this ACF and PACF plot. Okay, method is conditional sum of squares. And if you run this, you get the value of the MAR coefficient, the θ1 is negative. You can also do it with maximum likelihood, same order, right? And you get the values of the estimate, again here, the theta estimate. This is the intercept estimate. Actually, this is the mean, actually, okay, mu, right? Not alpha, mu. Okay? And here also you get the coefficient MAR, which is all close to each other. But the method of estimation is different. Okay, so we prefer this because it uses the maximum likelihood estimate, and it actually gives you a value of the AIC, which is the Akaike information criteria, which tells you which model to pick. So in this case, an Akaike information criteria is only available for ML. Right, so I will explain that later. Okay, there are large sample properties of the estimators. I will not go into that. All right, and so what happens if you fit a model which is too big? Okay. So for example, in the previous case, suppose instead of AR1 process, you fit an AR2 process. Then this is an example of overfitting. What happens is for the AR2 process, the variance of the parameters will actually just inflate. So it becomes a suboptimal estimation, statistically speaking. And the way to check overfitting is to use this Akaike, which is going to select the simpler model. So here is an overfitting example where I simulate ARIMA, okay, with the lag 1, okay, and the coefficient is this, right? And I fit ARIMA process with P equals to 1. This is the true model, and also P equals to 2, right? So you can see that everything is estimated. So in this case, the AR1 process is estimated by almost the true value. Over here, it is estimated there are 2 coefficients here. However, if you look at the AIC value, you see that the second one indicates overfitting. Okay? And the first value is the one that you should select because it's the smaller value, okay, of AIC. Okay? So parameter redundancy, for example, can be taken care of by preventing overfitting by using AR values. Okay, so if you have non-stationary data where you have a trend, in that case, you difference. So this is called differencing, that is D there. And then you can expect that it is going to be stationary. So this is what I did here, right? For example, in this example, I differenced. So there was a non-stationary process here. Okay, I differenced it. So that is D. Okay. So this one is called an ARIMA process. And the order of differencing, if you difference once, twice, thrice, is the order of differencing. And that is given by this representation here. So an ARIMA of differencing order D is you difference first the original series D times, and then you fit a ARMA PQ to it, which is this. So this is the form of the ARIMA model. You can predict, this is all prediction of ARIMA models. Okay, so let me just simplify here saying, or summarize. So to build ARIMA models, you do the following thing. You plot, first of all. Then you check for outliers. You check for trends, cycles, and variability patterns. For example, if the variability increases over time, that is an indication of non-stationarity. You can apply certain transforms like in the VARF glacial data. These are called Box-Cox transforms, which stabilizes the variance, and we use log. Then for achieving stationarity, you can apply d-order differencing. Okay, and many time series have this form, okay, where xt is related to xt minus 1 by a small percentage change. Right, so this is what we saw in the case of glacial data. Right, in that case, if you do the differencing of the logs, then this RT will be a stable process. Okay, and then what you do in order to identify, once you have differenced, you identify the order P, D, and Q using the ACF and PACF plots that I explained to you, right? And then you fit and then check whether the residuals are Gaussian or not. So you have to do residual diagnostics and check whether the residuals are IID, Gaussian white noise or not. Okay. This is a statistic that is used to test collectively whether all of the legs are significant or not. Okay. So you will just see an application of this. This is called the Jung box Pierce Q-test statistic. And the thing here is that the p-values corresponding to this test should be large so that you don't accept the, so that you don't reject the null hypothesis. The null hypothesis is that they are all white noise. Okay. So if you reject the null, then you haven't taken into account the correlation between the values. Okay, so here is an example where you have the log VARF data, and I show you the differencing. So I took the logarithm to stabilize the variance, and then I look at the differencing, which is difference of order 1, D, and Q, P is 0, and Q, because of the ACF, so I take the value 1. Okay, and this will give out variables called the residuals. So I look at the ACF and PACF of the residuals. So if this is a very good model fit, then all of this residual ACF and PACF should indicate the ACF and PACF of white noise. Okay, and clearly so you see this one is not too bad. Okay, and all of them are within the boundaries of 0 here. Okay, and similarly here, I know there are some values which are quite large here, but more or less all of them are here, but I'm still not satisfied because there is some lag at h equals to 1. Do you see here h equals to 1 for the PACF? This is very significant. So you haven't accounted for all of the correlation. So instead of PACF is is cutting off at a lag of 1, means that the value of P that you chose here is not right. So you should select P is equal to 1. Okay. So now what I do is, okay, so these are the residuals. Okay, if you look at the residuals and you look at the box test, you see the P value is very small. So the null hypothesis is rejected, meaning that the residuals are not IID noise, white noise. Okay, so we have to come up with a better model. So the plots here for the residuals give you an idea. So you didn't account for this, so you take the next one, P equals to 1. Okay. So now for P equals to 1, this is the codes that you fill, that you fit, and now you can see that this ACF and PACF look like the ACF and PACF of white noise. So this is a better model to fit compared to the previous model. Okay. And if you run the Jung box test, the p-value is large so that you don't reject the null hypothesis, which is saying that I think that it is IID white noise. Okay, so for finally, Dr. Mukesh, I hope I can go for 15 more minutes if it's all right for you. I'll finish this.
Okay, sir. If possible,
Is that-
complete within 10 minutes, sir.
Yes, okay, I will finish it in 10 minutes. So the next part is to do seasonality. For seasonality, as you saw, there was this periodic version, and now we have to take care of periodicity. So the way we take care of periodicity is also use differences, but we use seasonal differences. So in this period thing, we looked at seasonal differences, which was 24. So instead of taking difference, which is 1, you take difference, which is 24. Okay. So the again, you fit ARMA model for this kind of differences. So that is called a seasonal ARMA with capital P and capital Q, which looks like an ARMA, but now it is based on differences of the periodic of the period. Okay, hope that was clear. So the SARMA process looks like this. Okay, and again, the whole theory works the same. If you plot the ACF, as I showed you, it is periodic. And if you look at the ACF of PSCF of AR process and MA process, it shows the same kind of pattern. The ACF will cut off at lag capital Q for the MA process, and the PACF will cut off at lag P for the AR process. And all of these are multiples of the season or the period. The original ARMA, the non-seasonal component will still show the same. Okay, I'll give you an example later on. Okay. All right, so over here you can see that the period is 24 because look here, this one is very high. And then here again, the PACF, this is showing significant lags at units of 24. So you know that there's a period of size 24. So that is the SARMA model, okay, over here. So finally, we have the SARIMA model, which is the most complicated model that I want to show, where we incorporate differencing in the original time series model, just like in the ARIMA case, and also the big differencing D in the case of the seasonal components. So this is the final model that we want to do. Okay, so let me give you examples. For passenger data, you saw there was a trend and there was a cycle. So first of all, you can do the log transform to stabilize. Then you can look at the differencing, first order differencing. And then you can look at the differencing of order 12 because there's a seasonal component here of annual. Okay, and then we can plot it so you can see that the final value, plot here is stationary. Okay. And then for that final one over here, you can fit ARMA processes. So how to determine the ARMA? Over here, you can see that the first ACF is lag 1, okay, and then PACF is also showing lag 1. And these ones, you see here, these ones are the cycles, the seasonal cycles. So we have already modeled that, okay, but it says that the residuals still have this. So you have to model the P as 1, the capital Q as 1, and then the small p as 1 and the small q as 1, okay, because of this significant peaks. Okay, so we can try many models. Okay, we can try 1, 1, 1, 0. We can also try 1, 1, 0, 1, and we can try 1, 1, 1, 1, okay, based on the PACF and ACF plots. And then we can fit this, okay, and every time you fit, you can get the AIC value. And what you do is you choose the smallest one, okay? So the smallest one, this is minus 3.62, this is minus 3.67, and then you have minus 3.66 and 3.69. So look, this is the smallest value of the lot, and which corresponds to P equals to 0, D equals to 1, Q equals to 1, capital P equals to 0, capital D equals to 1, and capital Q equals to 1 and the seasonal component is 12. Okay, and then you can forecast based on that, based on this forecast function, based on all the mathematics that I have given to you. And this is the forecast. So the forecast will maintain the trend as well as the cyclical component, and also give you the 95% confidence interval. So finally, I want to conclude. I want to forecast TC values, right? So this is data that Professor Dr. Mukesh gave me. So you can read the data and you will see that there are cycles here. And we can zoom in and we can look at 7 particular or 8 days. And you can see there's a seasonal component, daily cycle here, right? So the most adequate model is Sarima, right? And so there is no need to take differencing because the models are already stationary. So there's no trend. There's no trend, okay? And there is seasonal variation. So you must take seasonal differencing. So t equals to 1. And I didn't take any ARMA components in the seasonal component or in the original component, okay? So now I get all the residuals and everything, and I see that the junk box statistics, the p-value is all rejected. So that means the residuals are not white noise, okay? So I know that this model is bad, okay? Now I have to determine what is a good value, or good P and good Q. So I go back to my ACF and PACF. So I see that these are the periods, okay? So I know the periods are there, but this is telling me that I have to take capital P as 1, okay? Sorry, capital Q as 1 because that's the ACF. And I've also got to take the partial ACF is also showing a lag here, okay, a peak here, right? So I have to take capital P also as 1 because these are corresponding to the periods. And if you look at the regular non-seasonal components, I can see here this is also increasing. So it's very high here, okay, this one, okay? So also I have to take Q equals to 1, and also I have to take P, which is this, the value of this is 1 here, high, okay? And this one is also high, but let's take all of them to be 1, 1, okay? So I do P equals to, well, okay, 2, okay? So because this is high and this 2 is also very high, okay, minus here, okay? So let's take 2. Okay, differencing, I don't take any differencing. I take Q equals to 1, and this one is all 1s. Okay, and then I get the output for fitting. And now I see that my junk box statistic are all p-values which are large. So the residuals are now white noise. Okay, when I plot the residual ACF and PACF, I'm happy because all of them look like white noise. Okay, so I'm done. So then what happens is I use the Sarima forecast. The Sarima forecast code, and I forecast my TEC value for the 8th day here. And you can see that the forecast is pretty good because it covers the observed data. And what you could see is that when it's upward, the trend is very easily captured. Okay, but if you see the peak has a lot of variability, because look at the peaks here, they are extremely variable. So the confidence interval actually captures the variability of the different peaks. Also here, this captures the variability of this downward trend because they are all very, very different for the previous 8 days. Okay. So that's all I have to say. Sorry for taking a bit more longer. Thank you very much.
Thank you, sir. Thank you very much for your wonderful presentation.
Thank you,
Participants,
Dr.
any queries are there, please? I think no queries are there because from since 2 o'clock they are attending. So
yes, I understand. So I'm sorry for taking a lot of time. I just wanted to finish everything. The slides are being recorded, so you can just refer to the mathematics if you want to. And the codes are also there.
thank you. Now I request our HOD madam to propose the vote of thanks.
I'm audible?
Yes, I can hear.
Good afternoon. Good evening, sir.
Good evening.
Good evening to everyone present here. It's my honor and privilege to propose vote of thanks to the chief guest of this session, Dr. Sarat Chandradas, sir, Professor Heriot-Watt University, Malaysia, for his enriching and thought-provoking lecture in statistical time series models for TEC prediction. Your insightful discussions on the time series data and the characteristics with examples, time series statistical models such as white noise model, moving average, AR model, ARMA model, ARIMA model, SERMA model, and SERVA model, and the estimation of mathematical concepts like probability distribution function, mean variance, covariance, autocorrelation, autoregression, autocovariance, PACF, etc. for the statistical time series analysis and forecasting has enriched our knowledge. The valuable research findings and the practical applications you shared will certainly inspire us using time series analysis in our academics and scientific pursuits. We are very much grateful to you, sir, for sparing your valuable time with us and sharing your expertise in the domain of statistical time series models for TEC prediction. At this moment, I would like to share that when we organized an international conference in April 2025, Sir has delivered the keynote address and also supported us signing an MOU with Heriot-Watt University, Malaysia, and also with our Sarnadan College. So this collaboration stands as an important achievement for us, opening new doors for research and academic exchange. We remain deeply grateful to you, sir, for your unwavering encouragement, visionary support, and continued association with our institution. Thank you very much, sir.
Thank you very much, Dr. Shanti. It's nice
Thank you,
to
sir.
see you again. And thank you very much for the note of thanks. And I'm very glad to do this. I hope everything was clear. The slides are very, very self-explanatory. So if there are any questions, you can always ask me.
Sure, sir. Our association will continue in future also, sir.
Yes, thank you.
Thank you, sir. Thank you. Dear participants, with this session, our 6-day online FTP program on navigation and Indian constellation, opportunities, challenges, and future developments has come to an end. Before we conclude, on behalf of Department of ECE, Sarnadan College of Engineering, I would like to extend our heartfelt gratitude to all who have made this event possible. First, we are thankful to Almighty for the blessings bestowed on us in successful completion of the program. Next, we are grateful to the management and our secretary, sir, for motivating us and giving freedom to organize this Atal FTP program by rendering the fullest support throughout this program. Next, my sincere thanks goes to our dynamic principal who has supported us and guided us right from submitting the proposal to AICT Atal Academy to till now for the smooth conduction of the program. My sincere thanks goes to our head R&D for providing valuable suggestions towards this event. I owe my thanks to heads of all departments for inviting their staff to attend this program. At this moment, I would like to express our gratefulness to AST Chairman, Atal Academy coordinators, FDP selection committee members for giving us an opportunity to organize this one-week Atal FDP program in our institution. We are very grateful to the following resource persons who have magnanimously accepted our invitation to share their knowledge in this FDP program. Professor P. Soma, former Deputy Director, ISTRAC ISRO, Dr. Ashish K. Shukla, Head Advanced Navigation and Science Applications Division, SCSC ISRO, Mr. G. Bharatidasan and Dr. S. Pratibha, Akkad Software and Systems, Bangalore, Dr. G. Raju, former Project Director, ISRO, Professor Jain University, Bangalore, Dr. D. Venkataratnam, Professor KL University, Andhra Pradesh, Dr. Anindya Bose, Professor, the University of Burdwan, West Bengal, Dr. B. Naveen Kumar, Professor, Osmania University, Hyderabad, Dr. A. Supraja Reddy, Associate Professor, CBIT Hyderabad. Dr. A.K. Sarkar, former Technology Director, DRDL Hyderabad. Dr. S. Ramesh Raju, Senior Manager, Honeywell Bangalore. Dr. Kavitha Devireddy, Research Associate, Manjeera Digital Systems, Hyderabad. Dr. Punyawi, Associate Professor, King Mongkut Institute of Technology, Thailand. Dr. Sarat Chandradas, Professor, Heriot-Watt University, Malaysia. I extend our heartfelt gratitude to our esteemed resource persons for their valuable insights on the evolution of NAVIC, its current applications, and the roadmap ahead have truly enriched our understanding. Their expertise have highlighted the significant role of NAVIC plays in strengthening India's self-reliance in satellite-based navigation and its vast potential in sectors like transportation, disaster management, agriculture, and defense. Their dedication to educating and inspiring us is genuinely appreciated. My heartfelt gratitude goes to our sincere, dynamic, and dedicated faculty members who contributed and supported us a lot in all aspects, without whom the function would not have become a successful one. My great thanks goes to our participants who have applied for this FTP program and actively attended the sessions. Finally, my hearty appreciation goes to our organizing committee for the smooth conduction of this 6-day Atal FTP program. Finally, as we conclude this FTP, let us carry forward the knowledge we have gained and contribute towards advancing India's capabilities in satellite navigation and technological growth. Wishing everyone great success in your future endeavors. Thank you and have a wonderful day. Audience, feedback please. Kindly unmute and give your feedback.
Good evening, ma'am. I'm Dr. Deepika from Rajarashwari College of Engineering from Bangalore. I just want to give one feedback, ma'am. Can I?
Yes, ma'am. Sure, ma'am.
Yes, ma'am.
Please.
Very well organized FTP, ma'am. So first of all, thank you from our end also. So on short time you have started, and 6 days it went well. And thanks the organizing committee for getting a very good resource person actually. So we got even the real time applications, even simulations, all those things. So enriched with so much of knowledge. Thank you so much, Mukesh sir. Special thanks to you also for contacting us and made us to join all this FDP also. Thank you so much, ma'am. Thanks Saranathan College for this wonderful FDP.
Thank you, ma'am. Thank you so much. Any other feedback, please?
Ma'am, good evening, ma'am. I'm Sheelavati from IT department.
Yes, ma'am. Yes, madam.
Yes, I would like to thank you for giving such a wonderful FDPs. This is very informative and eye-opening session for us. So, thank you so much for arranging this kind of FDP, ma'am. It's very useful to enhance our skill in research. Thank you, ma'am. Thank you so much.
Thank you, ma'am. Thank you. Any other feedback? This feedback will help us. Hindi job. Yes. We put your feedback in chat box also. And test will be available in AICT portal. All of you must attend the test. Any other feedback, please? Mahesh sir?
Madam, that's all, madam. We will conclude the session.
Okay. Okay, thank you. Once again, thank you all. All of you attend the session and give your feedback also. In chat box also you can give your feedback, and the link is also given in WhatsApp. So if, kindly fill up the feedback link also. Thank you. Thank you.
Thank you, madam. Thank you all.
Thank you.
Hello. Hello, good evening, sir.
Madam, good evening, madam. Solling, madam.
Sir, that paper is not opening, sir. I went to the AICT portal and I came to the assessment tab.
Okay.
And I accept that I have read, understood, and will adhere to the assessment guidelines. I have checked that box.
Okay.
And I click on that start. When I am clicking on that start button, it is saying that coordinator has not uploaded the questions.
Madam, what the thing is, you please log out once again, log in, because lot of what the thing is traffic, data
Server busy, I think.
So you please once again do it, madam. I checked with others. Lot of persons attended and got the certificate also. They sent.
You can take assessment at or after 8.
No, madam. Within 1 hour. You please do it now itself.
Okay.
Okay.
You are saying that please log in again.
Yes, madam. Again, log out and log it again
Sure,
and do it.
Sure, sir. Thank you.
Okay.